Okay, I think it's time to start the talk. Good morning, everyone. My name is Bowen Zhu, and I will be presenting our work on optimizing symbolic computation systems using a classic but powerful technique called hash counting. In this talk, we will look at its implementation in the Julia symbolics ecosystem and demonstrate its significant impact on performance and memory efficiency. At the heart of our work is a fundamental bottleneck in symbolic systems called expression swell. As we manipulate complex mathematical expressions, we inadvertently create thousands or even millions of identical subterms. For this mathematical expression, we write this piece of code, and its corresponding data structure is shown on the right. As we can see, there are some duplicate subtrees. For example, the term A plus B, C minus D, etc. So such redundancy leads to a cascade of performance issues, from excessive memory consumption to slower computations, because the system treats each duplicate as a unique object. And our solution for tackling this problem is hash counting. The idea is simple but profound. We never store the same thing twice. By using a global lookup table, we canonicalize every expression instead of a spreading tree with many duplicate branches. So we get a compact graph. Then with hash counting, the tree shown before was transitioned to the compact directed acyclic graph shown on the right in this slide. As you can see, the duplicate trees, such as A plus B, are removed. So this method not only saves memory, but also, very importantly, allows us to check if two complex expressions are identical by using a single lightweight pointer comparison. This takes only complexity O1 time. And our approach is as follows. We implemented this directly within the Julia symbolics ecosystem. A key part of our design was to make it seamless. We modified the core constructors, so any existing code that builds a symbolic expression automatically benefits from hash counting. We use the weak reference dictionary to work with Julia's garbage collector, and also we update downstream algorithms such that it can be aware of the structure directed acyclic graph, and turning such that adaptive algorithms can leverage the new structure. To test our work, we chose two challenging benchmarks. The first one is a biology model called the BCR system. This is a massive and highly repetitive. And for this problem, we expect big wins here. As for the second one is a physics model called XSTEAM. It is less obviously redundant about unknown variables. This allows us to see how hash counting performs across different problem domains. In our benchmark, we measure performance across the entire symbolic numerical workflow. including the time and memory used for computing the symbolic Jacobian, and also the time for code generation, function completion, and also the numerical function evaluation. For the BCR model, as we expected, the results are fantastic. We see more than 3-fold speed up in the symbolic computation phase, and we cut memory usage in half. By the way, in this diagram, the yellow lines correspond to the result with hash consing, and the blue line is the one without hash consing. And for downstream, the completion and execution were also twice as fast. This confirms that for problems with high redundancy, hash consing is a clear and decisive winner. The XTIN results are a bit more interesting. Initially, hash consing added a small amount of overhead. The yellow line here is the one with hash consing, and we can see the little amount of overhead. And the compiler was able to leverage its shared structure to produce incredibly optimized code. Code generation was 5 times faster, shown in this plot. And completion was 10 times faster. The final numerical evaluation is up to 100 times faster. So this shows the true power of hash consing. So it is not just in the symbolic construction, but also for enabling powerful optimizations later on in the symbolic numerical workflow. So after all, what does this mean? First, hash consing works, but its benefits are context dependent. Second, and also most importantly, we must look at the entire workflow. The massive downstream speedups demonstrate that hash consing is a powerful enabling technique for symbolic numerical computation. It proves that this classic software engineering technique is more relevant than ever before as we tackle larger and more complex computational problems. As for future works, we think the most exciting next step could be integrating hash consing with eGraphs to unify expressions that are not only structurally equivalent, but also logically equivalent. For example, 2 times x is the same as x plus x. So we can also make them the same object in memory for some purpose. Furthermore, we also explore ways to share our optimized structures in parallel and persistent environments. This is crucial for modern AI and HPC workflows. So in conclusion, we have shown that integrating hash consing into Julia symbolics is a real game changer, and it transparently reduces memory and also accelerates every stage of every pipeline of the symbolic numerical computation, from symbolic manipulation to the final numerical evaluation. So this work, I think, shows hash consing is an essential technique for building the next generation scalable and also efficient symbolic tools. Okay, thank you for your attention, and I'd be happy to answer any questions. Yeah, yeah.
Could you go back to the slide of like the comparison between the tree and the graph?
Okay.
For expanding the expression?
Do you mean this one?
Yes.
Okay.
I'm sorry, I'm just trying to understand it right now.
You might want to walk through exactly what the graph is displaying and how it correlates down to the equation.
Okay. For this mathematical expression, there are duplicate terms. As shown in this tree, for example, for this term, it is a plus b. And there is another a plus b here. So this is redundant. So hash constant removes this redundancy by reusing existing mathematical expressions. So in the updated graph, the term a plus b is reused here. Okay.
I have a question about doing this at the semantic level. What sort of challenges do you expect to see for doing hash consing based on logical equality instead of just structural equality?
Okay. Okay, you're asking what the challenges are for integrating it with logical equivalence. So the main use of Julia symbolics is to manipulate mathematical expressions and also generate efficient numerical code. So we would like to manipulate mathematical expressions that are most efficient and fast for evaluation in the numerical function stage. Does this answer your question?
Yeah.
Okay, thank you.
How would you, for example, show that like x plus 2y is the same as like 2y plus x for something like this? Do you have any ideas?
Sorry, could you say again your question?
Okay. How would you show, for example, like x plus 2y is the same as 2y plus x, because they're structurally different, but they're logically equivalent?
Yeah, so one of the things that is in the design of symbolics that I don't think was necessarily shown as much here is that symbolics uses a non-tree format. So there's a tree format for general terms, but there's also different formats that are for other formulations, right? So for example, when you're adding two objects, it's not actually going to use a tree formulation. It's going to use a set with hashes, right? And the reason for that is because if you use a set, right, then you don't necessarily have so if you say you have a tree, right, then you say, okay, I have a node and I have and then I have the part of tree 1, I have part tree 2, right? If you say that you have a set, you don't have an ordering to this array, right? You just have hashes to it. And the reason for this being unordered is because that's effectively encoding the commutativity inside of this operation, right? And but based off of the hash, it will then always order in the same direction, right? So you then have a natural, if you always put things into this form and it's always hashy, if the hashes are correct, are the same, then therefore it must be the same order. So it's naturally going to encode that by things that are two things that are by commutative operations that are the same, it'll automatically make those be equivalent. Same with associative operations as well. And so there's this kind of AC equality that's able to do for things that are like polynomials, right? So things that are adding, so things that are power operations. So there's a few things that have been specifically optimized in that form, and you'll see this in practice because if you do something like x plus y, you'll see that it automatically will give you y plus 2x, and you might say, oh, like why are you flipping this around or something? It's like, oh, this is the print ordering does not actually exist inside of the symbolic operation. It's storing it just as something that does not have an ordering, and so it won't even remember what your original ordering was because it's just saying there is an object here and it's exactly equivalent to this, so I don't need to store any information about that. And that ends up being a pretty major performance optimization in it.
Thank you.
Are there other well-known symbolic systems that are using consing? Like, when I think of symbolic systems, I don't know why, I always think of Mathematica as sort of like the big famous symbolic system. Do you know whether that uses this technology?
Professor, do you mean other symbolic systems that are...
Not the one in Julia, but, other systems that are out there in the universe?
I think the famous commercial ones are like Wolfram and Maple, and the open source widely used one is SymPy, implemented in Python, and maybe Search.
Sorry, what's the answer? Do you know if they're using consing?
Sorry, do you mean other symbolic systems that also use the technique of hash consing?
Yeah.
To my knowledge, there are comments that say some commercial ones, for example, Maple, that employs this technique, but there's no published results or any source code. And other open source symbolic systems have not yet fully deployed the mathematical canonicalization. So our Julia symbolic is the first one that published the quantified results of showing the benefits of hash consing for symbolic systems.
So this is a bit of a technical question that I'm asking as a user, and if you don't know the answer, I wouldn't be surprised. If I'm running a threaded program with like 20 threads or something, are there actually 20 currently? I'm asking about the current software. Like, are there actually 20 copies of this implicit hash table that kind of exists somewhere in the ether? And yeah, should I be worried in multi-threaded programs that, for instance, like equality comparisons might fail for some reason, or should I be concerned at all or careful in that situation, which is something that I am doing?
Yeah, so with the question about multi-threading, right? So multi-threading is both easy and hard because it's multi-threading, you have shared memory, right? So it actually is sharing the same object, right? Now the thing that you have to be aware of though is, if I make a modification to the object, so if I say modify the metadata, are all the threads aware that this metadata has been modified, right? This is something where actually when we first rolled out the hash consing system, we were like, oh yeah, we're so good, we're so fast and everything. And the first things that were found were multi-threading bugs, right? We worked through them. I think Ayush actually were one that worked through a lot of these with Oscar. So at this point, I think that we have the right locking and everything's in place, so that way it is multi-threading safe. But yeah, it is definitely a question that you have to ask about this. We've done some pretty extensive testing and we've done some pretty extensive analysis. We believe it's multi-threading safe, but because this was a piece that took a bit and it was some pretty hard work, there might be something here or there that we haven't caught, but at least we are pretty rigorously checking it at this point. It's a hard problem, but I believe we got it.
So for how long have this hash consing been used in symbolics utils and modeling toolkit? Because I'm thinking about whether I have seen the performance shift or whether I've not seen it when I've been using the packages.
We released the changes of hash consing roughly in April this year, just I remember. Yeah. Also because of the changes of hash consing in symbolic utils, previously in modeling toolkits, the option of common sub-expression elimination was turned off, but now it's turned on automatically, turned on by default.
Just out of curiosity, what kind of hash function and collision resolution do you use for the expressions that you have? Is it some custom hash function that you guys wrote, or is it like a generic one?
Okay, regarding hash function, the hash constant technique is independent from specific hash function implementation, as long as the hash function adheres to good hashing principles, such as uniform distribution. So we did not modify the hash function in this work.
Any more questions? Okay, thank you.
Okay. Finally, I want to thank my collaborator Ayush and also my colleague Sung Chen, and also the undergraduate student Blanca, and also my advisors, Professor Alan Adam and Dr. Chris Ruckakis for their support. Thank you. It's good to see you.
Sorry? Yeah, it's good to see you. Can I just take the mic in my hand?
We'll give everyone a minute here because, yeah, it's a.
Just as long as you're kind of behind the table.
Okay, yeah. Okay.
But you'd rather handle it?
I'd rather hold it. Yeah, that would be good. That's perfect. Yeah. Thank you. Is it presenting?
Oh,
It's doing something.
The air conditioning over there almost has the SIML logo.
No, did it just? Is it a wonky connection? It's gone.
Yeah, that's the AI created version of the SIML logo. It thought it told me that it was perfectly correct though.
I will just go. Yeah, it's still.
If you're having issues,
you know, it's kind of starting and stopping. Like it goes to full screen and then it quits, and then it goes to full screen again and then it quits again.
Now we got it.
We got it. Okay.
And do we got it on the stream as well? I know it was up there.
Yeah. It's a pretty cool building.
All right, might as well start.
Yeah.
So I want to introduce Ayush. So Ayush, I think a lot of people know the Modeling Toolkit project at this point, you know, as we're entering to V10. It's been a long project that's been going on with SciML, but within the last year or so, Ayush has really been actually the main contributor. If you check out the contributor graph, it's been his project. So here, Ayush is going to be the one to talk about what's going on with Modeling Toolkit V10 and all the new stuff that's going on and also the future of it. So take it away, Ayush.
Thank you. Yeah. So hi everyone, I'm Ayush and I'll be talking about what's new with Modeling Toolkit. And just as a preface, I'd like to say that I'm going to assume that people here have a working knowledge of Modeling Toolkit, but if you don't, just feel free to listen in and let me know if you have any questions. So before we get started, just a quick introduction about me. I currently work at JuliaHub and I maintain most of the open source symbolic numeric infrastructure that we rely on. So that's Modeling Toolkit, Symbolics, some amount of symbolic utils, and the surrounding packages. That's my GitHub ID, and I am active on the community Julia Slack in the SciML related channels. So if you ever want to reach out, you can reach out to me there. So the first thing I'd like to get started with is a feature retrospective of what we've built over the past around 1.5 years. And there's a lot of stuff to cover here, so buckle your seatbelts. First up is MTK parameters. This is one of the defining changes for Modeling Toolkit version 9. And what it really lets us do is have type-stable heterogeneous parameters. So we can have different parameters of different types. They don't even have to be numbers. So in this example, you can see that I have a parameter f there. It's a function that takes a real value and returns a real value. And it's any arbitrary function. I can use it in my code, so I can call it as f of t, or f of x, or f of 2x plus y plus z, or really whatever expression. And I can just create my ODE problem, and in my ODE problem, I'm going to say that f is sine. And I'm just going to solve it like any other ODE problem, and if I plot the solution, I get the time series out. And the really cool thing about this is you can just swap out the functions. So as in this slide, I can just swap out f for cosine, and it effectively just works. It just solves with cosine now. And this sort of swapping can also work during runtime. If you do it, for example, in a callback that just swaps out f for another function, which is pretty cool. Another thing that the parameter struct lets us do is parameter optimization. So we can solve for parameters against some experimental data. And so I have a really trivial system here, and it has 4 parameters, alpha, beta, gamma, and delta. And so you can see alpha, beta, and gamma are normal, and I've marked delta with this tag called tunable equal to false. So what this means is that I want to solve for alpha, beta, and gamma because they are just by default tunable, and I don't want to solve for delta. And so I'm just going to show the loss function really quick, and the loss function is pretty simple. All we're doing is we're taking the ODE problem, and this is the really critical line where I'm just, in using the SciML structures API, I'm going to say that I want to replace the tunable part of my parameters with x, where x is the optimization state, so the values of alpha, beta, and gamma that the optimizer is currently working with. And so I just swap those in with my parameter object. I put that into my ODE problem, get a new ODE problem with the updated parameter object, and then I can just solve it and calculate the loss against my data and return that. And so using this loss function, we can set up the optimization function and the optimization problem and give it like a random 3 values as the starting point, and give it a lower and upper bounds and all of the standard optimization.jl sort of workflows. And once I solve my system, so I can just do the same thing again. I can just take the solution and replace the tunal part of my parameter object with the optimized values from the solution. And voila, we have an ODE problem that we can just symbolically access and get the updated values of alpha, beta, and gamma from. And so this is something really cool that we've been able to make really easy with the SciML structures workflow and its integration with MTK parameters. Next up is initialization. So this has been one of the major continuing themes throughout Modeling Toolkit version 9. It took a while to get right. There's a lot of moving pieces and a lot of user-facing workflows that we wanted to make as intuitive as possible. So what initialization really does is it solves for the initial conditions of your system. So it's an ODE, a nonlinear system, so on and so forth. And so I've taken the classic pendulum example, and it's set up in a way that y and y prime are the differential variables, and we have the 3 other algebraic variables and correspondingly the algebraic equations. Now, traditionally, what you'd have to do is you'd have to specify the initial values for the differential variables. So you'd have to specify y and y prime here. But the thing is that this choice is really arbitrary, and Modeling Toolkit can change at any point in time, and you might change your model, and you might end up with a slightly different state selection, and then have to give a different set of initial conditions. And initialization just kind of makes that really easy. So in this example, you can see I'm going to provide an initial condition for x. So I'm going to say that x is 1 at the initial time, and the derivative of y is 0 with respect to time. And so, like, x is not really a differential variable here. It's an algebraic variable. But Modeling Toolkit is smart enough to figure out that I have 2 initial conditions, and I need 2 initial conditions, and I can solve for the rest. And as a user, you don't really have to do anything. You just give the initial conditions, you create the ODE problem, and we'll solve it, and it just works, which is really neat. One thing it lets us also do is ensure that your initial conditions are consistent. So for example, in here, I'm going to use a bad initial condition. I'm going to say that x and y are both 1, which of course is impossible because the string has a length of 1. So you can't really make it have a length greater than that. And the first thing that this will do is it'll tell you that the initialization system is overdetermined. So, and it's because we we only need 2 initial conditions. You've given 3. And so Modeling Toolkit is going to tell you that you probably have something is probably going wrong here. And if we still persist and try and solve it, well, it's just going to not solve. It's going to say that there's an initial failure, which means it couldn't initialize the ODE, which is exactly what you wanted to tell you, because you don't have a consistent initial condition, maybe because there's some default in your really large hierarchical model that you forgot about. Next up is polynomialization and homotopy continuation. So just as a primer, homotopy continuation is an algorithm for solving systems of polynomials and obtaining all of the roots of the system of polynomials, which is a reasonably common workflow. And so we have a SIML interface to that through nonlinear solve homotopy continuation.jl, and it just allows you to create a nonlinear problem and solve it with homotopy continuation as long as it is polynomial. Modeling Toolkit can generate code for this interface, and it can do a lot of really cool extra things. So like this is the system of polynomials that I'm trying to solve here, and I think you'll notice that the first one is actually a rational function. And in the denominator of the rational function, we have x minus 0.25. So while x equal to 0.25 is a root of the second polynomial, it's not a solution of our system because it's going to make the denominator of the first one 0. And if I just create the problem and use the homotopy continuation JL algorithm and I solve it, so in the solution, you're going to notice that the first element in both of the vectors is not 0.25, because Modeling Toolkit got all of the roots, and it was smart enough to figure out that, hey, I can't use 0.25 here, and it just ruled those out. Now we can also leverage symbolic solvers in symbolics.jl to make this even cooler. What we can do is we can recognize that some systems are not polynomial by themselves, but are polynomial in some non-polynomial terms. So here I have the exact same system, except instead of x and y, I'm using a and b, where a and b are some weird non-polynomial functions. And because we have symbolic solvers, we know how to invert these symbolic functions, and I can just solve my system and get all of the roots of x and y, because I just solve for a and b, and then I use the symbolic solver to invert the mapping and get the values for x and y. I have double the number of roots because there's 2 solutions for x for every given a. And I'd really like to thank Yassine and Alexander. They worked on the symbolic solvers in symbolics.jl, and they're really, really cool. So go check that out. Next up is FMU components. So this is Modeling Toolkit's interface to FMI.jl and FMUs. We can import FMUs in Modeling Toolkit and just use them as Modeling Toolkit components or as entire models. We support both version 2 and version 3 of the spec, and we support model exchange and co-simulation FMUs. We don't yet support the entirety of the spec, but we have a decent bit of coverage, and this is still a work in progress, so we're going to evolve this and add more features as we go along. So like, for example, this is a system of a spring pendulum from the FMI zoo, and if we just import it as a component, we can have the symbolic variables mass S and mass V. There's a little bit of name mangling going on, but that's, as I said, it's a work in progress. And so we can just solve it like any other Modeling Toolkit system, and we get out the time series solution. Another really cool thing that we've added recently is dynamic optimization. So we can solve optimal control and related sort of problems. So in this example, it's an ODE, but we have a cost and a constraint associated with it. So we want to say that the value of v at t equal to 1 it should be 0, and that we want to minimize the value of, maximize the value of x at t equal to 1. And so we can just provide those to the system, and we can simplify it, and we can say that these variables are inputs to the ODE, and this allows us to code gen to a variety of optimal control solvers. So we integrate with PyOmo, with Kasadi, with Jump, with InfiniteOpt, and with boundary value DFQ.jl. So it's just you just create a jump problem or an InfiniteOpt problem, and it just works effectively. And there's more. There's going to be more about this at a talk later in JuliaCon Local Paris. So go check that out. Now this is probably my favorite change. This was introduced in Modeling Toolkit version 10, and it's the new unified sort of system type. So up until version 9, we had like a really wide variety of system types, and so we had OD system that generates to OD problem and DD problem as a summary. We have a lot more, but so like this diagram really maps out like what systems kind of generated what sorts of problems. But if we really take a close look at it from the perspective of OD system, let's say. If you have an OD system and you add noise to it, you get an SD system. If you have an OD system, you add jumps to it, you get a jump system. If you have an OD system and you just forget about the independent variable for a second, structurally what you have is a nonlinear system because you can't take derivatives and things like that anymore. You're solving for fx equal to 0. And so discrete systems and OD systems are essentially the same thing. Like the discretes are just discrete time instead of continuous time. And if you combine them, you get what are known as hybrid systems, where you have some continuous time and some discrete time dynamics. And so it makes decent sense to just have them in one. Implicit discrete system is just the DAE analog for discrete systems, where you have some algebraic equations that require a nonlinear solver. And optimization system, as I demonstrated earlier, if you combine those with ODs, you get what is known as dynamic optimization. We can also just solve them on their own. And so this is why we kind of combined all of this and we ended up with just one system type. And the idea is an LLVM-esque architecture, I'd like to say, where you give us everything that's true. So like any sort of new, symbolic problem, you just tell us what's true about your model, and you create a system, and then we can generate a variety of, an ODE or an SD or a variety of optimal control solvers, and so on and so forth. And no mention of this system type would be complete without this quote from Chris in one of the pull requests, where we're really just talking about an optimal discrete continuous differential algebraic stochastic jump delay equations. And so I'm not even going to try and figure out what that acronym is, but I think if we get together, we can probably add a few more letters in there. So that's a project that I'd like help on. Another thing to cover is implicit discrete problem and improved symbolic callbacks. So as I mentioned earlier, implicit discrete is the DAE analog for discrete systems. Here I have the traditional Fibonacci sequence in X, and the second equation is saying that the exp of y is equal to X. I'm going to pretend that I don't know how to take the natural logarithm of this equation. So I can just create my implicit discrete problem, and I solve it, and from the solution I'm going to ask for x and the residual of the second equation, and as you can see, we get the Fibonacci sequence as the first element, and the residual is almost 0 throughout, which is exactly what we want. Now, why does this matter? This matters because we can do some really cool things with symbolic callbacks here. So I'm going to go back to our good old friend, the pendulum system. And what I'm going to change here is that I'm going to add an event where every 2 seconds, I'm going to say that the value of x after the callback is going to be some function of the value of x before the callback. So with v10, we're going to say that before the callback, the value of a variable is denoted with pre of that variable, and the value after is just the variable. And what this lets us do is just have a completely declarative semantics for what callbacks do. And it allows Modeling Toolkit to be able to figure out consistent state for the system after the callback. So if you're going to notice here, for example, that we're changing x, but x is an algebraic variable. And if you try and do this with ordinary DFQ, if you just have a callback that modifies x, well, ordinary DFQ is going to go, well, my algebraic variables are not satisfied anymore, x squared plus y squared is not 1, so I'm going to run brown full basic init, I'm going to make my algebraic condition satisfied again, and it's just going to solve for x, and it's going to reset x back down to the manifold, which is going to make it like the callback never happened, and it's just not what you want. So modeling toolkit just handles that for you. It ensures that the system is consistent and that ordinary figure doesn't do any funny things. And if I just create and solve the OD problem, so you can see that every time X sort of jumps up or jumps down, Y also correspondingly jumps up and jumps down to make sure that the system is satisfied and we still have all of those callbacks working as intended. Next up is common sub-expression elimination. So this is uses the hash consing work that Bowen talked about earlier, where now we're just by default generating really optimal functions for every single function that modeling toolkit generates. So here I'm just going to take a very trivial example where we have x squared plus sin x squared times t, and so x squared appears twice in the expression, but you can see that here we only compute it once, and we just kind of multiply it with t, and then reuse the same as a result from earlier to avoid having to compute x squared twice. And this applies to any sub-expression that's repeated in your equations. These are some honorary mentions. We've had like almost 100 releases since Modeling Toolkit version 9 came out, and there is no way that I can cover everything that that we've had going on, but there's this and there is more. So yeah. There's also some infrastructure level changes that I'd really like to go over. So not everything is code. There's a lot more to maintaining open source software. One thing that we've worked on really is improving the maintainability of our code. So we have, of course, the unified system type makes it just a lot easier. But for example, we've reorganized our workflow so that anytime you construct a problem, whether it's an OD problem or a nonlinear problem or a boundary value problem, we're going to go through that process simul problem function. And so it ensures that every time we construct a U0 and a parameter object, we're doing it the exact same way. And if we find a bug, we fix it for every single problem at once. And in a similar vein, all of the generated code goes through build function wrapper. It's an internal function. Please don't try and use it. But it ensures that any optimization that we do to our generated code is just applicable everywhere across every single function that Modeling Toolkit generates. There's also been a bunch of work around CI and testing to make sure that Modeling Toolkit is, continues to be robust and reliable. Every pull request, every bug fix adds a test. We run tests against Julia LTS, latest stable release of Julia, and the latest pre-release of Julia to make sure that we're forward compatible and we know about bugs in newer releases when they, as soon as possible. We also now test against release versions of downstream packages as opposed to just against the master branch of those packages. This is currently only set up for Catalyst, but of course we're open to doing it for more packages as we go along. We also test against more upstream functionality, so places in packages like ordinary DFQ or SIML sensitivity where they use Modeling Toolkit in their tests, well, we run those tests from Modeling Toolkit to ensure that we don't break those. And a new addition is the benchmark CI, so we run a few benchmarks to ensure, like for example, OD problem compile times don't just go through the roof because, spoiler alert, they did a while ago. There's also been some improvements to documentation, so we have much better internal documentation. A lot of our internal functions, especially the newer ones, have doc strings. We have all of the utility functions have doc strings. We document all of the keyword arguments. And we have a new developer documentation section in the docs, so anybody looking to contribute just knows a little bit more about how things work internally. We also have a new API documentation section with Modeling Toolkit version 10, and the goal here is that every single public API function has a doc string that documents both the public and the non-public API of that function. And we leverage Julia's extended help functionality to sort of hide the inner details from the user in the REPL. And the API docs just list out all of this. In fact, we've run into issues with Documenter trying to erroring out because our pages are too large. Just to wrap up the presentation, I'm going to talk about what's next for Modeling Toolkit, what our goals are for the future. Of course, in continuing in the vein of documentation, we want to rework our doc pages. We actually have a discussion ongoing about this. So the goal is to rewrite it for a newer version of Documenter because the original docs are written for a very old version of Documenter that doesn't have all of the nice things that it has now. There's a new structure that we're going for where there are tutorials that really hold your hand through common workflows and tell you explain like every little bit of what's going on, as well as a separate section for examples, which are just really just snippets of code that show what's possible with Modeling Toolkit and a sort of common user workflows that people might encounter and the best ways to do them. And of course, the aforementioned API documentation and developer documentation that we're always working on expanding. There's also been significant effort that's been going into and will continue to go into improving scaling. So one of the first things on that list is support for array expressions and array equations. Anybody who's used arrays enough in Modeling Toolkit has probably run into that warning. That's a very annoying warning. And we, like as a summary, we're just trying to make it go away and really support arrays as first-class citizens in Modeling Toolkit and throughout our symbolic numeric stack. This ties into the next goal, which is to integrate with reactant.jl, which will allow us to generate really performant array code and target a variety of architectures with it. So to be able to deploy and solve our systems on like GPUs and stuff. There's also an ongoing rewrite for the core of symbolic utils.jl for improved type stability and performance, as well as to make arrays first-class citizens, as I expressed earlier. So just huge free speed up for everyone without really knowing what's going on behind the scenes. That's always nice. We're also looking into like really specialized code generation pipelines. So for example, one thing that's going on right now is semilinear ODE problem, where if you have a differential system that's expressible as sort of a linear transformation of your state plus some nonlinear term, so AX plus some C function of X, we can, typically this happens in PDEs, where your discretized PDE has a really big linear part that tends to be stiff, and the nonlinear part tends to be sparse and non-stiff. And so we can split that out, and we can generate a split ODE problem and target our implicit-explicit split solvers, and just get a huge speed up without you as a user having to do much other than add 4 letters or however many letters to the beginning of your ODE problem. There's also a bunch of just other new features that we're working on adding. The first one is analytical integration. So for several trivially integrable expressions like this one here, we can just integrate it for you and remove it as something that the integrator has to handle manually. There's an ongoing GSOC project to add symbolic integration to symbolics.jl, which we really want to leverage here. And for the things that we can't integrate, but we really don't want to have the OD solver handle, we can always use integrating callback from DiffEq callbacks, for example, and just have that have the transformation happen automatically. There's also something that I really like to add is the support for symbolic structs. So essentially just record types in symbolics, where you have a symbolic variable that represents a bunch of values with the fields, and you can just use get property to access those fields and get a new symbolic value that represents that field. But yeah, that's essentially it. Thank you, and I'm open to taking questions.
All right, thank you so much. Does anyone have any questions? Hands up for questions. All right, Helmut.
Hi, very nice talk. So how is the delay differential equation interface modeling toolkit coming? Are you working on this?
Sorry, the latest version of?
Delayed differential equations?
Yeah, so delayed differential equations, we do support those. They do work. I'm sorry, I didn't quite get, like, how are they coming along is what you asked? There are some, it does work. I mean, and like it's sort of there. There are a few things I guess we'd like
to add. Most of the issues I think that you would have had would have been solved with the system unification with the modeling toolkit v10. Yeah. So one of the issues with the delay differential equations before was it kind of sat in the space of like, oh, you don't really have a delay system, so how is it handled? With having one system type, it's basically able to say, okay, I can handle these delays. Oh, if you have stochasticity, this is where stochastic things go. Da, da, da. So stochastic delay differential equations and delay differential equations got pretty much, a lot of bugs worked out just through the fact that we simplified out the system behind it.
Right. Yeah. Thank you.
Any other questions? Yes, Sebastian.
You mentioned something about running MTK on the GPU. Can you talk more about that? Like, would it?
Sure. Yeah. So this is still like, just as a disclaimer, this is still a ways off. I mean, we need like array support and then be able to target reactant with our code generation. But reactant is a package that uses LLVM and MLIR to be able to generate really efficient array code, because that's what MLIR is really, really good at doing. And the idea is that we can just we can generate functions that are really friendly to reactant, have reactant take that, trace through the function, and generate the optimized MLIR, and then have that MLIR be compiled to a GPU kernel or to something that can run on TPUs, for example, or and stuff like that. So ideally, as transparent as possible, just generate the code, ask reactant to do something on it, and solve the problem.
Yeah, I will say that modeling toolkit code for ODEs does generate on GPUs. I think I made that the documentation for that last week or so actually go live on the latest stable version of DiffyQ GPU. Modeling toolkit with the differential algebraic equations currently does not build for GPUs for the kernel methods, because the kernel methods need to have support for the initialization process, and that currently is not GPU compatible. I have a Claude agent trying it out though, so we'll see if it ends up being done by the end of JuliaCon. Any other questions? Any? All right, we got a question right here.
So how large of a system would you sort of think is reasonable to model with modeling toolkit? So is it 1,000 ODEs, 10,000 ODEs? What's like, how should we think about it? And is there any advantage of using modeling toolkit for extremely large ODEs?
Great, yeah, thank you for that. The definition of a large system is continuously changing, and of course the goal with all of the symbolic stuff is to make large systems smaller. So I think right now, off the top of my head, I would say that if you're getting to a couple thousand equations, that's sort of when you're really hitting the limits of modeling toolkit and hitting those structural simplification runtime issues. That said, one of the really big advantages of using modeling toolkit is that it is common sub-expression elimination for these kind of large systems, where suppose you have like a system with like 1,000 equations. Usually, if you simplify them and you remove the aliased variables and like analytically solve for some of the subset of variables, I have seen systems like the extreme system from Bowen Stock, which it turns like around 100, 1,200 equations into some 100, 1,200 equations into something like 300 or some that the integrator actually has to handle. And the generated code for that is gonna reuse all of the common sub-expressions. So you don't have to generate some, like actually manually write all of this kind of messy stuff where you're not computing x squared twice, or you're not computing if else x is less than 3 x squared plus 2y plus z multiple times. It's just gonna generate that for you. And as he showed in his talk, it's an easy 100x speed up for that sort of code gen, just without having to do anything.
Yeah, well, and so there's a few things to mention. I think that with what you're just saying right there, we should meet with Bowen. I just realized that there's probably an algorithm that we can have to be able to make it so that way they can regenerate loops. So let's talk about this at lunch. But the other thing is that the semi-linear ODE problem, I think that's one thing that's kind of a bit understated right now. So what we see when people say like, oh, I have this gigantic system and it's very difficult for modeling toolkit to compile, right? The reason is because it treats everything as nonlinear. But the majority of your equations are actually just linear or quadratic, right? So one of the things that we're doing with semi-linear ODE problem is that we're pulling out the linear part and the quadratic part to say, this is just a matrix, this is just a matrix, and so those parts are handled O of 1, right? And so then it really, when we start to say, so, we're saying like, oh, currently modeling toolkit, modeling toolkit before started to choke at about 1,000 equations. Now with hash consing, it's starting to choke about 5,000 equations, right? But now we're changing the definition. We say, oh, 5,000 non-linear terms of equations. Any equations that you just have linear terms, they don't count anymore, and any quadratic terms, they don't count anymore. So something like BCR, or these a lot of these chemical reaction systems, the vast majority of his mass action terms no longer count in what we count, right? And so, there's kind of this like, when we're saying like, it's always going to be a statement of what is the current limit of modeling toolkit, but I think that, one of the key things to kind of note out is that, we're trying to find these special forms, especially linear, quadratic, stencils, so all these things that cover PDE operators, so that way they can be handled in a specific way, and they count as O of 1. If we handle those as O of 1, yeah, you can still write down a whole bunch of, nonlinear terms like, x to the 2.5 power, like, okay, that doesn't fall, but you can do 1,000 of those and you're okay, is that fine, right? So we're starting to we're continually trying to find what are the repeated common patterns and specializing on those, and that seems to be the most helpful approach to the scaling of the problem.
Just to quickly add on to that, I think a couple of versions ago, we have a simplification path that actually improves runtimes by a lot. And it was based off an observation that a lot of times people add variables to their model just because they want to be able to observe those variables. So you might want to, maybe for your model, something like x squared plus y is a term that you'd really like to observe. So you create z is equal to x squared plus y. And you don't use z in your equations anywhere. So there's no reason it should actually go through the simplification process. And we're able to just take out all of those equations early and reduce the number of equations that we actually operate on, which actually has a huge impact on the performance.
All right, so we're coming up on time. So thank Ayush for his great talk.
Thank you.
And next up, we will have Dr. Chris Rakakis. I think I've met him before. Can you be the one to do the questions, I guess? I'll pass it on. Sure. Oh, no. All right. Well, if that's not going, then try it with this. Yep. All right. Thank you very much. I'm just going to get started right away because I know that I'm going to want to go over on time on this one. So this talk is a talk that I think is kind of crucial to what we're doing because, we've worked, so what has the SciML organization been doing, right? We've started a lot with numerical methods, and we kind of started doing a lot with the scientific machine learning. And then this whole symbolic thing came up, and I think a lot of people have been kind of like, don't you work on numerical methods? And I think, I've always been saying like, oh, we want to do symbolic things because they'll build us a better numerical solver than we could ever do by hand, right? And I want this talk to really show you exactly what we're doing. It's, I would say, still in progress. The things can still be used. We haven't turned everything on by default, but I want to show you what exactly is going on in the ecosystem so you can know, where are we getting the next 10x, where are we getting the next 100x of performance, right? So let me start with a quick introduction to SciML and our numerical methods, right? SciML is an organization that has these differentiable numerical solvers that are highly optimized for all sorts of different systems, right? This is actually just one subset of them, right? The linear solvers, nonlinear solvers, differential equations, which has ODEs, SDEs, optimization tooling, integrals, and things for partial differential equations, right? So this is what you kind of know and love of the numerical part of SciML. And this is the part that we've really kind of developed over the last 10 years. This is kind of our core, right? When people think about SciML, the first thing that they usually will go with is they'll say, oh, differential equations.jl, right? This is the thing that was 50x faster than SciPy, 50x faster than MATLAB, it has all those benchmarks. But the key that really made it so that way, it was not just another ecosystem was when we started being able to show that, here's this performance improvement over the C and Fortran methods, right? When I actually started a lot of this, I was told, oh, nothing will ever beat, LSODA. Nothing will ever, ODEs have been done. It finished in the 90s. And what we found was, there's a new numerical methods that could do this, right? There are numerical methods that were already in the literature. There's new things that the way that computers are being built changes the way that you have to build algorithms, and we really kind of brought this forward with all these new solvers. But as you continue to do that, we're still continuing to make numerical methods, but that tends to saturate, right? You start to be able to say, oh, we're 2 times faster, 3 times faster. No longer you get the 100x all the time if you're trying to start battling against yourself, right? And so, what I want to do then is I want to kind of introduce like what can we start to do in a very hands-on kind of way, right? So let's take a problem that is kind of simple, right? So here's a linear system. We want to find the U1, U2, U3, U4, U5 such that this system is satisfied. U1 equals U of 5, U2 equals cosine U of 1, right? It's some nonlinear system. And I think most people here, like you got your laptop out and you're like, all right, I know how to solve that system. You write it down and you put it into a Newton method, right? That's what you do. So it's a system of five variables, and you want to solve for 5 different variables in a system of 5 equations. You throw it into a Newton method, right? And okay, so that's what we did. We as an organization that works on a lot of numerical solvers, we actually just got a publication. I think I got the email that was accepted a few days ago, but I didn't read the full email. So, I think Avik said though it's now accepted that we have this publication now that shows nonlinearsolve.jl is by far the fastest nonlinear solver. It's outperforming MinPack. It's outperforming Sundial. So we've done this not just for ODEs but also for nonlinear solving. With these tricks of trust region and other ways of doing Newton methods. So you just call a Newton method, you just make it good. One of the things I want to highlight here is that again, these algorithms have been really optimized over the time. So when we say we're doing better, we're saying when it's head to head, we maybe have like a 1.5x speed up, a 2x speed up. It matters a lot because a lot of people are doing Newton methods, but it's not going to be that huge changing. Well, where the huge changes come from end up being these compiler integrations though, where we say, okay, you give me a code, I will find your sparsity pattern for you, and I'll determine whether I should use a sparse solver or not. And if you didn't know that you should use a sparse solver, we will turn it on and boom, now you get a major performance gain, right? So we get a lot of gains through these kind of looking at your code and automating things, but the numerics is still kind of saturating because how much can you do with the Newton method, right? So, but we do, yeah, go ask a question. Yeah, so the question, I think your microphone is muted, but the question was, does this hold across a bunch of different problems? So what we had to do for this paper is there's actually a whole test benchmark, which is 23 different nonlinear problems that is from a test set that we pulled in. There's also a lot of other problems pulled from industry, right? So one I'm showing here is a DFN battery model and its initialization, right? And we've also collected a lot of problems from the organization, from people in the community. So if you go to the SciML benchmarks, you can see that there's, it's benchmarking a set of 35, 40 problems. And our methods do not do the best in all cases, right? But on average, over, I think that in 37 of the 40 problems, we are now doing the best, right? And for the other 3 problems, that becomes its own research project. Okay, what do we do there, et cetera, and continues on. But yeah, if you think that you're on your problem, we don't do good, please just submit that as a pull request to our benchmarks, and so that way we can see how bad are we doing on that benchmark. We want to see that because then we'll spend the next few years making it better, right? And that's effectively why we do well in the benchmarks, right? We look at this every day and we just say, you wake up in the morning and say, how could I do better on this benchmark? And then you go say hello to your dog or whatnot, right? But it's always, how do we do better on this benchmark, right? And so at this point, again, you could wake up, you just say, this is a Newton method. I put this into nonlinear problem. And if you've seen the nonlinear solve talk or the documentation, you just write it down where you just say the residual equals, move everything to one side, you call nonlinear solve, and boom, you solve it. Done. This is what everyone does, right? C does this, Fortran does this. We have some good numerical methods, but everyone does this. So what else could we do? Well, what if we were human, right? If I was a human and I was like to look at this problem, I would not solve it by trying to find all 5 variables at the same time, right? What would I do? Well, what I would do is I would say, well, look at the first equation, u1 equals u5. Let me just substitute that into the other equation, right? So u2 equals cosine of u1, so therefore u2 is equal to cosine of sine of u5. And if I just start substituting things together, what I'll find is that there's an equation at the end, which is u5 equals gigantic mess of only u5. This is a scalar equation. But if I solve this scalar equation, I can substitute everything else together, and ta-da, I'm done, right? So if I was a human, I wouldn't solve 5 equations at the same time. I would just solve this one, and I would do everything from that. And so what we started to do, we say, okay, how can we put what the human smart person would do and put that as part of the numerical algorithm? This is symbolic numerics, right? Where you say, okay, give us the structure of your equations, and we're going to actually modify the equations, and we're going to compile something after we've changed your equations, and we're going to do the numerics on a changed form of that equation, right? So symbolics and modeling toolkit come before the numerical solver. It comes before the differential equation solver, the nonlinear solver, or any of these pieces. So you've taken the whole ecosystem and made it so that way there's a symbolic part that could go in front of it. And so what we can do now is we can say, hey, here's a symbolic representation of the nonlinear system. Now simplify it for me, right? The simplified version of this equation system is one equation, and there's 4 other equations you can derive from that. And now when you solve the equation, it only gives you out one value, right? Because even though you gave it 5 equations, it solved 1 equation, but it just knows how to generate all the other solutions from that, right? So now we can be kind of smart, right? And the question is, how much did our brains actually help? If we actually look at what's going on inside the Newton solver, right? The Newton solver uses an LU factorization, which is O of n cubed, right? So as you make these systems harder and harder, the cost numerically grows like cube, right? So if we make that system smaller, then we don't just like, if you half the size of the system, you don't half the computational cost. You take the computational cost by 1/8 down, right? It's an order of magnitude just by decreasing the system by half. So this really means that, okay, even if we can just start to simplify out even small parts of it or something, we can still get major performance gains just by saying, oh, this is an easy part, this is an easy part. Right? But then we can also start to do other things, right? We can say, hey, look, here's a big system of equations. And if I was a computer, I would say, let's run a Newton solve on the big system of equations, right? But if I was a human and I looked at this problem, I would say, the first 2 equations only use U1 and U2. So let me solve that first. And if in the next 3 equations only use U3, U3, U5. So let me solve that first. And then the last one uses all the equations, so I'll solve that using the results of the first ones. But not only that, but the last one is linear, so don't call the Newton method, just use a linear solver instead, right? Like if I was a human, I would look at this and I would do this on the whiteboard, and I would say, oh, the reason why numerical methods don't work well in my domain, quantum physics, is because people have realized that we have to specialize the equations like this. No. The problem is the numerical methods should be specializing your equations, and if you're just putting it into a numerical solver, it won't. So what can we do here? Well, what we can do is we can make it so that way we have a set of this new SEC nonlinear solve, which says, here's a way to be able to do this cascade of nonlinear solvers, where you can say, solve the first problem, solve the second problem, solve the third problem using the results from the first and second, and actually make that one linear, and tie it all together, right? So now we can do these cascades of problems where you say, hey, look, this is actually the more optimal way of solving it, split it apart. And then what we can also do is we can make it so that way the modeling toolkit front end, the symbolic front end, does this analysis, figures out how to cut everything up, and splits it for you, right? And so this is what we've been able to do. So this has been a standard part of modeling toolkit for a while, right? And we're continuing to prove. So as Ayush had mentioned, right? We're continuing to improve this, where you can start to say, hey, look, symbolics.jl now has a symbolic ODE solver, right? Or a symbolic nonlinear solver. So if you give it polynomial equations, it can try to find if there's a symbolic equation. And so now we can start to say, hey, look, let's cut this into little portions, right? You solve this one, then you solve this one, then you solve this one. Does this piece have an analytical solution? Oh, if it doesn't have an analytical solution, what do I know about it? Can I transform it into a polynomial system? It basically tries every little trick that is in the literature. I think everyone always says, oh, you have to use your, I have to write my own code for the way that I do, my chemistry domain, because I know how to make these things solve better, right? Well, every single trick that you do, we can stick it into the symbolic system and automatically put that in front of the numerical solver, so that way it tries it, right? And so we're just growing and growing and growing with these terms. And so this is why we're talking about symbolic numerics, right? These are things where people say, you can't just use the numerical solver. And I think we agree that you can't use the numerical solver, but we don't agree that it can't be automated as part of the numerical solving process, right? And so all of these little tricks, all these different analytical solutions, we're then piecing it together as part of this pipeline for the solver. And now the next piece here is to say, okay, this has just been about how you solve a nonlinear system. Let's go back to ordinary differential equations. Can we use this so that way we can build an ODE solver that is doing so well that people will effectively accuse us of cheating in benchmarks, right? That's my goal. I want people to ask this question, like, are you cheating in your benchmarks? Because if we are doing so well in our compiler that it is, finding your sparsity pattern and doing all these things that people are like, oh, but SciPy isn't allowed to do all that, so is that really apples to? I want it to be a non-apples to oranges comparison, because that's how you're going to get the best solver, right?
Can I just make a funny observation here? This point about cheating in benchmarks, I think one of my grad student from my days, one of my advisors, I was literally told that Chris Rackauckas and his gang are terrorizing people at conferences with their data.
Yeah.
This is a real complaint that I have received.
Yeah. So I mean, yeah. So if our solver is faster on this equation because we replace the numerical solution with an analytical solution, you know, people do accuse us. Oh, you're cheating that benchmark, and I say no. Make your algorithm go faster, right? This is a valid thing. The analytical solution is true, so we're using it, right? And I think that, you know, so that was without ODEs involved, right? Now, how do we bring all of this to the ODE domain so that way we can continue to cheat even better, right? So in order to figure out how to do this, let's take a quick primer on implicit solvers, right? So an implicit solver, if you want to solve a differential equation, the simplest one is the implicit Euler method, right? UN plus 1 equals UN plus h f of UN pt, right? And you say that, oh, you know, if you go to a stiff system, you have to use this kind of solver, and because it's good for, you know, systems that are stiff, that have large eigenvalues, yada, yada. But, you know, okay, but UN plus 1 shows up on both sides. So what do we actually do inside of this equation, right? Well, what we do is we move everything to one side, and we say, hey, if we know the previous step, UN, we know our step size, we know the parameters, and we know Tn, then all that we're solving for is UN plus 1. So we need to solve an equation, G of UN plus 1 equals 0. I just told you, that's a Newton method, right? So what every single nonlinear solver, what every single ODE solver does today is they say, let's take your system of ODEs on that exact function, and let's solve a Newton problem for that whole equation. But like, should you actually do that? I just told you all the different tricks that we could do if you had a nonlinear system. Here's a nonlinear system. This is the slowest part of our stiff ODE solver. Can we just change that as well? Right? So here, let's take an ODE. So here's the Robertson equation. You know, we show this many, many different times. It's a chemical reaction system, right? So anytime you're going to solve this, you're solving for 3 ODEs. And so every single time you have to solve a Newton method for 3x3 systems. You know, so you have O of 3 cubed as your cost, yada, yada, right? But let's do this little bit. What I'm doing in here is I'm basically saying, hey, symbolically go through and generate the exact same equation that is being used inside of the nonlinear solver for the FBDF method, and now run structural simplification on it. And what it does, if you look at this equations line, I don't know why my pointer's not showing up. If you look at the equations line, it says the equations for the nonlinear solve in the middle of the step there is I can actually solve it by just solving for one variable, and I get all the other ones for free. Because it did, you know, again, I just told you all the tricks that it's able to do. But if I take this simplified version of the nonlinear solver and I stick it within my FBDF method, right? If I inline in this nonlinear solver and outline the ODE solver, I can then use this simplified version of the numerics. And now it's specializing it specifically only to your solver, but it's now turned it into a problem that is, you know, from 3x3 systems to 1x1 systems. And again, the cost of this is cubed with the size of the system. But not only that, we can actually do this in a form where we can say, if you use this form, mx plus outer TMP, and we rewrite the ODE solvers, then what we can do is we can make it so that the modeling toolkit can generate exactly one form of a nonlinear system and make it so that way every single ODE solver is able to use that exact nonlinear system. So we can compile one piece of code that is, hey, here's the optimized form of solving this weird piece right here, and then every single stiff ODE solver goes, hey, in my internals, I can reinterpret what I'm doing to be that piece, and do you have an analytical solution for me? Do you have a optimized piece for me? And then we can use that symbolically numeric generated piece in the middle there. And so effectively, what we're then able to do is, for this system of 3 equations, we're actually only solving one set of equations at every single step and knowing how to interpret it back up to 3. So now, again, yeah, we're cheating because we're only solving one equation and we're getting all 3. And this is what we now have as the NL step interface. So in Modeling Toolkit, this is not done by default yet because, again, there's still a lot of moving parts to this ecosystem. But if you tell it NL step equals true, what it'll do is it'll generate this nonlinear system. It will simplify it down. And then you can tell it to use certain ODE or nonlinear solvers. Again, the nonlinear solvers that you use here are the nonlinear solve.jl ones, right? Everything in the ecosystem is piecing together. And now you can say, hey, solve this with FBDF. And so the first order, second order, third order, fourth order, fifth order BDF. It doesn't matter which, as it's adapting its algorithm, it's always going to use this optimized version of the nonlinear solver because of the way it's being retargeted. But not only for FBDF, you move it to an SDirc method, it's also going to use this. You move this to Rado method, well, the Rado methods will need a little bit more, but it could also use this, right? And so basically what we've done then is that we made it so that way the symbolic ecosystem is able to reach into the middle of the ODE solver, find its most expensive piece, be able to reconfigure it and simplify it down for your specific problem, and then inject a function right into there so that way during its solving steps it can use that optimized piece. Again, there's still a lot more to do here. So this all works, right? This is all working code. This is, the tests are all on and everything. I think that what we still need to do is we still need to do some performance improvements because there's still some allocations going on in the way that we're shuttling things between different solves. And so we need to make sure that we fully do out the caches and we fully do out the way that we do the reuse steps. But what we see already is we're already seeing, even though it's allocating, it's already faster for a lot of cases. And so once we get all the performance improvements in, we should be doing quite well. One of the other things that we haven't done as well is as I mentioned, we can cut things up so that way, instead of solving one big problem, we cut it up into 3 problems. It turns out that we cannot do this chopping up in the middle of the OD solver right now. That's just because of some things within the interfaces. Specifically, SCC nonlinear solve needs to have a caching interface where you can define a nonlinear solve once and then change the parameters and just reuse the same caches over and over. That interface does not exist. So like the integrator interface on nonlinear solve, that does not exist on the SCC portion right now. We need to fill that out and then but these little details in the middle just to really make it so that way all of the tricks and all the SCC portions can be all applied within the ODE solver, and then we'll be coming out with our the major benchmarks. But the thing there is, yes, it will look like we will have cheated in those benchmarks, and I think that it really depends on your definition of cheating. I believe that if your compiler can do all this automatically and can replace your entire numerical solve with a bunch of analytical solutions, I am happy to say that that's how we do it and get on my level. So, continuing the R&D, I think that there's a lot more that's going on in this space. Alexander Demmin, I think, is one person I'd like to highlight who's been doing a lot of very interesting work in being able to not just on nonlinear systems, but also find out how to be able to rewrite ODE systems as equivalent forms. So that way, instead of solving, here's a case that's really easy to identify, where instead of solving 4 ODEs, you can solve these 2 ODEs. If you mix this with the way that we do the nonlinear solving, you can end up with solving a scalar equation for the set of 4 polynomial or differential equations. And so, if you start to mix all these different tools, you start to have ways to use analytical solutions on this part, and they could all be quite different. And again, I just want to highlight another thing that Modeling Toolkit does that you should be aware of. There's a lot that we're doing for performance, but a lot of this actually doesn't just matter for performance, but also for numerical stability reasons, right? If we replace things with analytical solutions, we no longer numerically require that, hey, if the Newton method converges, then x squared plus y squared equals 1. When we do these analytical solutions, x squared plus y squared equals 1 is built into the analytical solution of the system, and it cannot be broken. Right, so you start to get a lot of these features, like like conservation of energy is just a result of the system because we do not have the numerical solve that causes the drift and the numerical error in these kinds of properties, right? And this is also mixed with a lot of things in Modeling Toolkit, where you can say give it a differential algebraic equation, and it can then change it to a different differential algebraic equation, which is numerically easier to solve. This is the DAE index reduction pass, right? So again, we're mixing things that are specifically for improving the stability of the numerics with things for analytical solving, with things for simplifying down the systems that are being solved, and then also cascading them into multiple systems. And I think that this is the way forward, right? I think that this, the promise of Julia was that we don't have something where the compiler lives separate and you write numerical methods on the compiler. This is something where we started to say, hey, it invites numerical people to start working with the compiler, right? Multiple dispatch means, hey, use multiple dispatch to write your own compiler and integrate with the system. And if you're to give a numerical analyst a compiler, this is the cookie they come up with, right? And I think that this is still something where a lot of new projects are going on. In fact, everyone who's thinking about, oh, I want to work with MIT in the Julia Lab, all of them, I'm telling them, we do a lot of scientific machine learning, but the scientific machine learning integration with symbolics, this is what this is really the future. And so if you want to talk to us about projects, we have a project list, and we'd be happy to start getting you in these collaborations, because I think that these kinds of techniques are everything that is going to be down the line, all the major pieces. So thank you very much.
So I have multiple, let's say, devil advocates questions, right?
Yeah.
One is there are situations where actually extending the problem simplifies the numerical solution, right? So homotopy methods and stuff like that. And like biasing the search to say we'll always try to reduce things symbolically is you're trading off continuous optimization with discrete optimization, right? Symbolic search is essentially discrete optimization. So are you sure, and have you seen this in your benchmarks, that going via symbolics always, like in total computation time, always reduces the complexity?
It doesn't always. It doesn't always. Yeah. But also there's again. You make this statement that says, oh, there are some cases where you have to use homotopy methods, right? A, Modeling Toolkit can target homotopy solvers, right? This is one of the things that Ayush had talked about, right? And B, my question to you would be, what kinds of systems would you do this on, right? What would you look for inside of a system where you'd say, hey, let's target a homotopy method instead of the other method?
I'm asking the questions here.
Well, yeah, but if you give me that, then we have a way to target the homotopy methods, and we will just do that, right? Like, this isn't something you say, like maybe you should try this. The algorithm can be look for that property, and if you have that property, generate for a homotopy continuation problem instead of nonlinear problem, right? Yeah. And so I think that if you think about it in the wider, yes, there's certain algorithms that we're doing here, but if you think it in the wider symbolic numeric mindset, right? I think that your problem's not actually a problem. It's more of like, what's the algorithm, right? Well, you got to do it to the microphone, so that way the beautiful, beautiful viewers online and in the video and the ones who live on YouTube could hear as well.
Sounds good. Just following up on that question, though, because as you're kind of, in some problems, you're switching computational complexity from the solver to the simplification or structural simplify.
Yeah.
And is the solution for that, and I'm have in the back of my head like polynomial systems, and sure, once you find like a Grosvenor basis, you're done, right? But you've switched all the computational complexity to that. But so is your solution for that just finding some way to identify like the dispatch in the structural simplify that you bake in to that? Anyway,
yeah, being able to identify, is this useful, should we do it or not? Yeah, that could be based off of heuristics and benchmarks, but also just generally making that part faster, right? The first talk in the symposium was the hash consing talk. The second one was the modeling toolkit talk, and they all talked about how we're identifying shared structure and making systems simpler and improving the simplification passes, right? It really goes hand in hand, right? That we really need to make the symbolic simplification needs to get better. In fact, the compilation of the functions that we generate from these analytical solutions, that needs to get better. And we need to piece all those together in order to get a system for which this all makes sense. See, that's why I mean that there's a lot of moving parts, right? There's these parts of like, if we start to do all these integrations and we're generating this function and we're inlining into the solver, is the solver compatible with Julia C? And can you precompile to a binary still, right? Like, how do all of these things need to be answered in order for it to actually be a good, snappy system, right? So yeah, there's in some times you're trading numerical performance with compile time, right? Does this make sense for your given problem? I think that what we plan to be doing is we plan to just be giving all of the knobs, right? With heuristics on top, right? That's what we generally do with the differential equations and everything, right? We say, here's 400 solvers, but here's a default, right? We're planning to do this with the whole symbolic numeric system where we say, here's a structural simplified, but you can also tell it, NL step true or false, or allow analytical solutions true or false. And it'll basically look at it and go, yeah, if you have a partial differential equation with 2,000 equations, I'm not going to go through and try to analytically solve every equation in here, right? But maybe you'll try to analytically solve, small sets of equations and such, So it's a game of ever improving heuristics and ever improving, I think the key here is to really kind of structure this then as something where you say, okay, we have these different parts of the system, the numerical methods, and we're really exposing, hey, there's a system in the middle here for doing transformations, and what we want to allow you to do is we want you to be able to, we want to put every single pass possible in here, and then we want to put heuristics on it, but then allow you to control this piece, and then improve modeling toolkit, improve symbolics, improve meta theory, the symbolic utility. We just need to continue to improve all these layers, and whichever ones tend to be working in the end, these are the direction that the heuristics push people towards, right? So, and this is why I kind of say this is kind of an open-ended talk, because there's one direction that seems to be working really well right now, but again, there's a lot of other things, for example, using E-graph simplifiers, which we had I think Alessandro had a nice paper on a few years ago. Bringing back some of these E-graph simplifiers is also one other technique I haven't even touched on here that can also improve a lot of these systems, right? So there's a lot of these different techniques at play. There is a trade-off always when you do these, that you might be doing more analysis up front. So yeah, if you want the lowest latency version, probably doing the classical numerical approach of just throwing in the solver is the best. But if you know you're going to be, say, putting this into an optimization loop, for example, one thing that we haven't quite done yet, which we're definitely going to do though, is, hey, if you want to do reverse mode automatic differentiation on your piece, right? If you do a stiff ODE and solve going forwards, you also have a stiff ODE solve going in reverse for the adjoint method. Can we take the ODE that's generated by the adjoint method, take its nonlinear solve and simplify that down too? I mean, if you're waiting 4 days for your optimization to solve, maybe you're willing to wait 5 hours to be able to get a really nice one, and then generate a binary from that, so that way we keep that function around, and boom, just slam through all these optimizations, right? So it's always a use case thing, and there's a lot, and I think that what we need to do is we need to just get it out as good as possible, and then enable these different use cases to be able to say, hey, I care about latency, I care about making it as fast as possible, I care about numerical performances, and these will all require different kind of paths through the system.
Sounds great, yeah.
Right, do we have any other questions for the speaker? If not, let's thank Chris for the fantastic talk.
Test 1, 2. 1, 2.
Is it on?
Yes. Oh, just be careful. So. If someone hits this, just need to make sure that it's on. So that happens, and I don't think there's a way to we'll just have to keep an eye out.
Yeah.
Start. I had just one on for most of the could you hear everything okay with just one of these on?
Yeah.
The last session? Okay.
Yeah,
Because I know we
that's
shut them
fine.
all off at
Yeah,
first.
yeah.
So I'll turn off 3 of them.
Okay.
Right
Yeah,
before
yeah.
we start.
Okay.
I'll let it cool down
Okay.
as much as
Okay, thank you.
Yep. Have you seen the presenter?
No, not yet.
Hey, hey, sure, okay.
Make sure you're kind of as close as you can get to this. I'll turn 3 or 4 of these off, which will help with audio a little bit.
Sounds good.
Yeah, kind of as close as you can get to the mic.
Okay. Hey everyone, because this is the first talk in this afternoon, so we will wait for maybe another 2 minutes for people to come. Okay, so let's get started. Today I will talk about Taylor diff, which is implementation of higher order automatic differentiation and about its applications. So because we are in this symbolics and numerics track, I will specifically focus on how to use symbolics tricks to make this better. This is the outline. First, I will talk about what is Taylor mode AD and how we implement that. Specifically, how we use symbolics to automatically synthesis rules for higher order automatic differentiation. And then we will talk about several applications like solving nonlinear equations and ODEs, which many of the Julia community should be interested. And so first part, let me just give some background about higher order derivatives. So for a function that maps Rn to Rm, the full derivative of it has like m times n to the power of p elements. So it's often prohibitively expensive, but actually many applications don't actually require that full derivative. And so we focus on a specific type of higher order derivative, which is the higher order directional derivative. So if you are familiar with AD, you all know that what is a Jacobian vector product. It is just f prime x times v, and you can extend it as to second order, which is called Hessian vector product, and you can extend that generalize to multiple orders, and we will use the bundle notation f0, f1 towards fp to be the higher order derivatives immediately contracted with several vectors. So these are called directional derivatives. If you try to do this with nested forward diff, well, it's doable. But the mechanism that forward diff achieve that is it will create a dual number pair for each order of this differentiation. So when you nest it again and again, it will double the numbers of operations each time you increase one order. So it's like 1 times, 2 times, 4 times, 8 times. But actually, Taylor mode is another technique that try to do the same thing with much faster speed. The technique here is how we can build such an automatic differentiation system with higher order chain rules. Because if you learn about the first order AD theory, you will notice that the core principle here is the chain rule. So if fx equals to g of h of x, and you know the function value of h and its derivative, and you know the chain rule, you can always propagate over the function g and get what is fx and what is f prime of x. Okay, and in order to do that, you need to define a lot of building blocks, which is known as first order primitive, or also called first order derivative rules. When you have all these rules and building blocks, you can actually have a robust automatic differentiation package that handle a lot of different function definitions. And similarly here, for higher order AD to work, we just need a equivalent of chain rules in higher order contexts. Technically, it is known as Fadi-Bruno's formula, but I will avoid using this name. Just call it higher order chain rule. And as you expected, higher order chain rule is capable for propagating H0, H1 towards HP using our bundle notation to F0, S1, and Fp. And fortunately, for all the elementary functions as well as many special functions, we have some recursive computational tricks to evaluate the higher order chain rule very quickly. It is guaranteed to be at most O(n) squared, and in many cases linear, which is a lot better than the exponential case when we see in nested for first order differentiation. Okay, and then just a very little demo on very simple functions, but you can see that for these simple cases, you do see nesting the first order derivative is quite slower than just do this all at once with Taylor mode. And then let's talk about some implementation details. There are two different ways of viewing the differentiation problem. When you represent the bundle F0 to Fp, you can have a single array that first put all the elements. So imagine you have an array of elements. You can store the various order of derivative of the first element, or at one block, and then for the second element, and then for the nth element. But you can also have a separate array for each order. We will call these two things scalar mode and array mode. The benefit of doing scalar mode is that you always have a contiguous memory chunk for the whole array, because the order p is a compile time constant for your function. And actually, the forward diff is always working in this way. But this have some disadvantages, because in order to do some linear algebra on such arrays, you cannot just call into BLAST or LAPACK. You need to use the generic linear algebra routines defined in Julia base, which is not always optimized. So it should be good for nonlinear operation dominated function body, but may not be as good for linear operation dominated. And we get some inspirations from a package called ForwardDiff2, which is developed by Ma Yingbo, which is a previous Julia Hub employee. And so we will introduce the array mode in Taylor diff, and so that we can do both scalar and array mode for this higher order differentiation. And for both scalar and array modes, as I've mentioned before, the order p is a part of Julia type. So that using the Julia multiple dispatch mechanism, we can always specialize on the type parameter, and we can always stack allocate all the values and derivative partials, especially beneficial for the scalar mode, where then you will have a whole contiguous chunk of memory for this bundle. And this will also allow some more aggressive optimization, such as unrolling the loops in the primitives. And this is what previous AD packages like Taylor series.jl in Julia, which roughly do the same Taylor mode algorithm, but not as efficient as this implementation. Okay, so there's a quick demo of what I said before. When you construct a Taylor scalar, which is capable for propagating derivative up to like 2 order, and then you evaluate it on the exponential function, and it just boils down to very simple scalar operations, which should be efficient in Julia. And it doesn't need to allocate memory or have some very special instructions. No, just simple math. And we can demonstrate how powerful this specialization is with Taylor series.jl. If we go to Taylor expansion of a considerable order like 20, you can see that in each of the examples, it is quite a bit faster than Taylor series.jl, which don't have specialization on the order parameter. And what's more importantly, we just said that how we can handwritten some rule for maybe the exponential function and maybe a couple of more, but we definitely don't want to write all the higher order rules, or we call them primitives, to support our differentiation, because we already have a library of rules, which is called chain rules.jl. And chain rules is used by many AD packages, like Zygote use that, Diffractor use that. I'm not sure if Enzyme use that as well, but okay, Enzyme maybe not using that, but anyway, if we can find a way to automatically make use of these rules in higher order context, then it will be very easy for library order to maintain the rules. So the trick is like this. We start with the recursive definition, which is g of h of x to the derivative of nth is like g prime hx times h prime of the n minus 1th order derivative. And then you can expand this with like the multiplication rule of high order derivatives. And in the end, this recursive definition will lower the expression by 1 order. And so you can always recursively evaluate that, although this is not very efficient. However, we can always unroll this recursive definition at compile time with Julia metaprogramming. And if you define all the primitives like this using symbolics, symbolics is just like a mini compiler in the Julia language. You can always transform this kind of rules at compile time, so that in the runtime, the functions are already compiled and simplified, maybe doing some common substitution elimination. And then you will get very efficient higher order primitives, although it comes from the more involved recursive definition. So in short, okay, the formatting is a little bit clunky, but if we have first order AD rules in chain rules.jl and we have symbolics, then we can synthesize higher order AD rules in tailordiff.jl. Okay, and then we will show some applications of this package. The first is nonlinear equations, which many should be familiar with. The first order solver is just using Newton's method. You compute the Jacobian and solve a linear equation and apply it to the vector x to update it. And we have the second order generalization of this Newton solver to be called the Halley's method. And it's a little bit more involved, but what's notable here is you have the term f prime prime x dot a, where a is another vector. Okay, so if you don't use higher order Taylor mode derivative, then f prime prime x may be not very computationally tractable, but it's very efficient in iterative.jl. So you just need to do this with no more than 2 times of the evaluation time of the original function f, and then you can construct this Halley's method. And because of higher order solvers requires fewer iterations, even in large-scale problems, so as we demonstrate that with the discretized Chandrasekhar's integral equation, you can see that the speed up of using higher order method is actually bigger when the problem size is larger. And this is generally not true if you compute the full derivative, because the full derivative doesn't scale well with the problem size. Okay, and it can also be applied in the context of ODEs. For example, we have a ODE defined as u dot is f of u and t. There is a method called Taylor integration, which is just try to expand it, like u is a Taylor series and f is a Taylor series, and you plug into the ODE and try to determine, okay, for each order of t, the coefficient at left-hand side should be equal to the coefficient of right-hand side. But if you try to do this, you will instantly hit some problem, which is the definition of this ODE is actually recursive, because f is a function of u. So when you relate the various order of coefficients of the left-hand side and right-hand side, you will get something like u m plus 1 is the nth order coefficient of f, but f actually depends on u, which means that you at least need to know u0, u1 up to un to calculate this fn. So this is really not something that you can handle it with just one call to automatic differentiation library. The naive algorithm is like that. You first have u0, and then you compute f0, and then u1 and f1, and blah, blah, blah. But each time you get f, you need to invoke a call to automatic differentiation library. So it is like O(n) squared complexity. This is definitely worse than the state-of-art ODE algorithms. For example, we have some Runge-Kutta method, which is not as expensive as this. So if we just do it naively, then the Taylor integration method will not be better than other well-established ODE methods. However, we can do some simplification. And it's worth noticing that there is a previous package called Taylor integration.jl, which is based on Taylor series.jl, and it defines a very specific macro called Taylorize. So if you have an ODE function, you can actually manipulate on that and try to handle this recursive definition explicitly and reduce all the redundant computations, redundant allocations to synthesize a more efficient function body to compute the all the coefficients un, so that you got a local solution near time t. Okay, this definitely works, but it's hard to implement because it is full of macro tricks, metaprogramming, and a lot of restrictions. And if you read the documentation of them, they will notice that this doesn't work in all cases. And it also doesn't make use of existing Julia infrastructure like symbolics, because symbolics, if you imagine that it's just a mini compiler inside the Julia language, so it is already very powerful, and it should be capable of handling this very simple case. So symbolics here can help to track the full computational graph on F. So with symbolics, we can have the full representation of computation happening in the ODE function F, and then directly transform it to a function to output the F0 towards Fp, and then you can get U0 to UP for an order P integrator. Okay, so, well, this is a little bit out of the canvas. But anyway, this is just a work precision diagram where you solve the same equation with different, okay, maybe let's do it more, okay, so that you can see the whole plot. So we compare it with some state-of-the-art Runge-Kutta methods like TSIT5, version 6, version 8. And you can see that it is outperforming the method by the state-of-the-art method by quite a bit. And this is generally not true if you just use the naive implementation of Taylor integration. So it's symbolics that makes the Taylor integration method better. And of course, this is not very, this is just an initial attempt to develop these integrators. And the next steps, we might need to find some implicit method for stiff system. It could also be beneficial. And also, we can do adaptive order integrator for complex dynamics. So if you imagine that if you implement adaptive order for Runge-Kutta method, it's not very straightforward because each order of Runge-Kutta is very different. You need to do the tableau again and again. But for Taylor mode, each order implementation is very similar. You just need to vary the order parameter P, and all the different integrators will just be compiled very seamlessly. Okay, so this is all for my talk, and I'd like to express my thanks to my collaborators, Bowen, Keming, Jiacheng in the Julia Lab, and also thank you, Professor Alan and Dr. Chris. Thank you. Welcome any questions.
Any questions?
Sure. Oh, where is? Okay.
Awesome. Thanks for the talk. I didn't catch the first part, but I'm just curious, have you tested this code or had reason to test it with outside of just like real numbers, say with like complex valued functions or things along those lines? Because that's something that I'm interested in with code, is like generalizing ODE solutions to hyper-complex number systems.
Okay, this is actually a great question. Right now, the Taylor diff package only, it will work with complex numbers, but only the analytical functions where you don't have something like z bar. So in this case, you can just treat the complex numbers as real numbers. And so if you want to handle this more generally, we might need separate treatment for like the real part and the imaginary part, which is not currently there, but we can definitely try to find some way to maybe utilize the rules defined in chain rules to achieve this for non-holomorphic functions.
Awesome, thank you.
I'll admit I'm probably not an expert or anyone that truly understands what you're showing here that much, but do you have some real-world applications that you can cite that you're specifically using this for, whether it's some form of chemical analysis, trial analysis, inclusion or exclusion on sets or something like that?
So there is a more complicated example in the paper related to this work where we apply this to the Bruce-Slater's problem, which is a chemical reaction diffusion equations, which contains high frequency and linear diffusion part and nonlinear reaction part, and the ODE solvers to solve this equation is like implicit solver because it is very stiff, and in order to do this, there is some nonlinear solving within this stiff solver, and Taylor diff-based Hellis method can actually accelerate the nonlinear solve part of that specific problem. In that, I'm not sure if this level of application is what you are interested, but you can definitely check out this paper.
Yeah, that answers it. Yeah, that's what I was looking for. Thank you.
Also, like from the ODE side specifically, these are getting integrated into ordinary FEQ, and as if these continue to work well, we might start using them as default methods. We're a long way from that. These are still in implementation stages. But eventually, this might be what happens when you call solve in an ODE, in some cases.
More questions? Okay, thank you.
Okay, thank you.
I'm going to just practice and make sure my stuff connects. I'm not on till 4, but it looks like nobody's going to be here for the next few hours.
Yeah, I was just checking the schedule.
Yeah, so
Looks like yeah, not until 3.
right. Okay. Now it looks like we have plug-in power somewhere.
Yes.
Okay. Do we plug into the wall, or do you have something else that you prefer?
from what I checked, but let's wait a couple more minutes to see when they show up, and then we get started, okay?
Yeah, yeah. I'm here every o'clock. Every o'clock. I got one. I needed, yeah, I needed power, and I needed the adapter. The HDMI directly didn't work.
Oh, that's right.
Oh, there's the power. Perfect.
Let me be right back.
Other way.
Okay, okay.
Hello, everybody. Welcome to one more session at the JuliaCon. So let's welcome Dr. Akaukas for the talk, Optimal Uncertainty Quantification of SciML Model.
Yeah, thank you very much. So this has been a long-going collaboration with the Air Force Research Lab between MIT, Air Force Research Lab, and Julia Hub. We've been working with Adam Gerlach and his group for now like 4 or 5 years. It's really evolved into something which I think is very useful to a lot of applications. So what I want to describe today is what optimal uncertainty quantification is, the libraries that are being developed, what it kind of are doing, but also an idea of what they're useful for. So I'm going to start with like a really nice example problem that exemplifies what it's all about. So here's a picture, right? Imagine you have a seesaw and there's just a bunch of sand on the seesaw, right? There's some distribution of sand, right? But you know that the seesaw is balanced, right? And the question is, what is the maximum amount of sand that is to the far right of the seesaw? This is the question, right? So there's some possible distribution of sand. So any possible continuous function distribution, what is the maximum amount of sand over here? You think, oh, that's impossible, right? But we do actually have one piece of information. If the seesaw is balanced, then the forces on the left equals the forces on the right. So what can we do with that? Well, if the seesaw is, one thing that we can look for is what is the worst case scenario? Well, what is the way to get the most sand on this seesaw? Well, what we could do, right, is we could say, okay, there's some distribution of sand, but if I want to be able to get more sand on the seesaw, I can make it so that way it's pushing down on the left more, right? Because if there's more force over here, then I'll be able to put more stuff over here, right? And how can you get more of a force on the seesaw? What you can do is you can push it as far left as possible. So push all the sand to the left. And if you want to also make it so that way the force on the sand on the right is also, as low of a force, you push it towards the middle as much as possible. So there's this continuous distribution, but the worst case scenario, or the scenario where we can put the most sand on the seesaw, is where we put all of the sand over at 0 and all of the sand at the furthest point to the right where we're measuring from, and we say, how much sand can I put in that case? And that is the maximum amount of sand that I could put to the right of, for any possible distribution of the sand, that's the maximum amount that could be to the right of that point, right? Now, why is this a question that we'd be interested in? Well, it turns out that you can do a lot of worst case probabilities as this kind of problem, right? So for example, let's say we want to build a flood barrier, and we want to be able to say, what height for the flood barrier should we have, such that there's a 99% chance of being safe? That turns into a problem of saying, over all possible probability distributions that satisfy certain properties, how do I make it so that way every single probability distribution, there's only 1% chance that something can go wrong? And that's exactly the same problem, right? Where any possible distribution, I want to find the percentage of being in the bad portion. It's exactly the same problem. And now it's weird because it's like, oh, over all distributions, how is that solvable? But like what I described is that even though we're looking over all possible distributions, the worst case scenario can be described as, oh, you put sand in 2 parts, right? So it turns from this huge continuous problem into a discrete optimization problem. And it turns out that that's a general principle that you can prove. So you can show that finding the worst case distribution turns into a problem that you can do a discrete optimization. So here's the problem, right? We want to be able to find the probability that something happens, given that we know, the expected values and variances, and we want to be able to find this probability over the space of any possible distribution that satisfies those expected values and variances, right? So, why are we doing this, right? Why do we not just do Monte Carlo simulation? Well, if you do Monte Carlo simulation, you have to assume, oh, my parameter uncertainties have this distribution, and and you push things forward and you say, there's this percentage chance that something goes wrong, right? But that's not enough for safety critical applications. We want to be able to be certain, right, that if I say that the average wind speed is 3.5 and the variance in wind speed is 4, then I want to be able to say for certain that I know that for any possible probability distribution, there's less than a 1% chance that the plane will fall out of the sky, right? And this is exactly what optimal uncertainty quantification lets you do. So you could basically build this system in a modeling toolkit-like language, and what it'll do is it'll generate an optimization problem that is this discrete optimization problem that finds the worst case scenario distribution and tells you whether the worst case scenario satisfies these probabilistic constraints. And if you satisfy that, then you know that for all possible probability distributions, you are safe. And so what we're able to do is, this is for the flood barrier problem, we're able to say, oh, if the barrier height is 2.0 meters, there's a 17% chance that you can have a flood. But if you make the flood barrier 4.6, there's a 0% chance that for any probability distribution that satisfies the mean and variance requirements that we put down, that it will be unsafe. And you go, okay, that stops flood. How can you also do this with dynamical systems? So what we've then also done is we made it so that way you can connect this to all the dynamical systems modeling, and then you can get these flow through the dynamical system models and apply the same optimal uncertainty quantification tool. And from this, then what you're able to do is be able to make statements like, if you only know the starting point of the plane, there's a 31% chance that the plane will hit a wall. But if I know the mean and I also know the variance of the wind, I could certify that there's a 0% chance for any possible probability distribution, right? No probability distribution has more than a 0% chance that it will cause an accident, right? And so this is something that you can actually then certify. We're able to do this with certified global optimizers. It is a very difficult numerical problem, but we've been scaling it and we're continuing to improve this. So you'll find this as optimal uncertainty quantification.jl in the SciML repos, and this is something that we believe can change how people will do safety critical analyses in the future, given that it can certify, 4 uncertainties for every probability distribution, whether something is safe or not. So thank you very much.
Thank you for the talk. We have time for one quick question.
I wanted to ask about the guaranteed optimization results on dynamical systems. If there's something that, like, can we guarantee that, like, that optimization results on a dynamical system is in a certain...
Yeah, that's a great question. So it's a very difficult problem, right? Because the numerical solvers have their own error, and we want to make sure we account for that error. So what we're able to do is we're able to use reachability analysis tools and Taylor models to be able to bound the error that comes from the ODE solver, and then we're able to, so that way that's taken into account, and so then we get a flow that includes, the possible uncertainty quantification of the uncertainties of the parameters and the bound that includes the numerical tools, and be able to bound, given all of that together, does what you're trying to do, certify that the planes, the two planes will not collide given uncertainties in the wind, right? And so, yeah, we're able to take that all into account. That means that it is ridiculously computationally expensive. This is hard to do for very large systems. We call large systems in this space about like 10 variables, right? But we're working a lot on the scaling and the GPU aspects and such because it has this very strict property of guaranteeing safety. So.
Thank you so much. For the sake of time, let's thank Chris, and you can find him around and ask more questions.
I'm everywhere.
Oh, yes.
I can just take it if not.
If you escape out of that.
Yeah. Already mirrored.
Sometimes it makes you do it again.
Okay. Sounds good.
So for our next talk, we'll have challenges and opportunities of performing path planning for healthcare robotic systems with the Julia language. So let's welcome our speaker.
Thanks. Good. So it won't be too techy, but let's try to get it. That's me. Just a note that I'm working at Siemens Healthineers. So it's a healthcare branch of Siemens where we do all this imagery, machine, and also advanced therapies. I have some background rather in aerospace industry and modeling and simulation. This is the co-author. I wanted to make a slide with everything, but when he told me that basically he won four times the world champion at RoboCup, I thought that was enough as a slide. So I won't put more. And we are doing quite some robotic there, so it makes sense to have him on the team. I'm going to introduce the problem we are going to solve, how we have solved it so far, and it's two approaches, one static and one dynamic. And then I'm going to say, okay, why we are trying to solve it differently and go with some results, and mostly perspectives. Conclusion is one sentence. So the problem we want to solve is this staff shortage in the hospitals. We have really problems where all the physicians and nurses, they have a lot of workload, and we basically want to make things simpler for them. And if you look at this machine, it's able to do like 3D scan with X-ray. So you have some kind of like dancing between these two parts which emit the X-ray on one side and receive it on the receptor on the other side. And if you want to automate all that, then you can save a lot of work. You can say, I want to target this part of the body for my imaging. So basically you want to say, go there, and the machine goes there. But also we're looking into helping the assistants in the lab with some robotic systems. And that's a research project that we've done with all the names that are there, and the robot that is actually
Here on the left is Aurora, and it's actually like a robotic arm that can bring you like some materials on the scene. Good. And there are some problems. As soon as you want to make things autonomous, you want to make sure that you go from point A to point B without colliding with people or machines, and that's what we are going to talk about today. So the first thing we did is to do something really, I don't want to say basic, but like it's really static in the sense that we discretized, well, we basically imported a map of the floor, of the room, we discretized it, like meshed it, and then we did like some A-star path planning algorithm, which is static. And as you can see, for example, here you have a system which is like this rectangle, let's say it's a bed going to an MRI system, then you see that at the end, the behavior is basically not necessarily physical, like the rotation at the end is actually not something that the bed can easily do, and it's like super heavy bed, and you can have super heavy patient on top of it, so it's really hard to maneuver. On the other side, it's super fast, like you just compute the thing in 20 milliseconds, 50 milliseconds. For a really long pass, it's like 100 milliseconds, it's still like super fast. But we wanted to be a bit more physical, so what we did in the first place is we did a Modelica model. And based on this Modelica model, we wrote an optimization with the Optimica language on top of it. And we used dynamic optimization using Casady to basically optimize for the path without colliding with the objects. It's physical, like all the motion is basically constrained by the physical behavior of the system. So that's something we can do. And it's really not fast. So that's the drawback here. So we get things, but we cannot like put it on the product, like on the hardware itself, and using it for the path planning, right? Like it's upfront. So you can get it why we want to try new ways, where we want to actually to do something that would be fast and that would be physical. And well, as you see, we had like two parts. One part which was really algorithm-based, and the other part which was more physical. And we basically believe that with Julia, we can have all that. So at the moment, I'm using Modeling Toolkit and Julia Code. And well, I believe that with Dyad, we can also like get even simpler with the DSL that it provides. And then we can actually do the model physically with the Dyad language. And the goal is to be fast and physical, right? So the first implementation we did is basically adding a fun stuff on top of what we have done so far. So we take the map. We basically compute a cost based on the map, which is a function of like the distance to the wall and so it's 2D for the distance. And the third dimension is basically the angle of the system you have. So if it's a square, it's kind of easy, but if it's a rectangle, then you have like, for some angle, you have to have more margin basically before colliding to the wall. So that's part of the compute cost. So we have a 4D at the end cost map because you have the cost as a fourth dimension. We compute, the image is just the same, just in different perspective. We compute the path with an A-star algorithm so that we get a first initial trajectory for our dynamic optimization. And this dynamic optimization runs at the moment with modeling toolkit.gl and Dyad control systems.gl for the optimization path. I have the name of the function from Dyad if you're interested, but I forgot about it. In first result, where it's really, really fast. Like compared to what we had in Modelica plus Optimica, at the moment, I think we have a factor. In the abstract, I write 5, but from what we got in the latest, it was even faster. Like we got like below the second for the compute, and I think there is lots of things we can still optimize there. It's a great feeling because you code basically the algorithm, all the pre-processing, everything, and the physics in the same language. That's really something that basically avoid you to have like this barrier between the two languages. There are some minor drawbacks, which is more like on the change of culture. Like usually we had this two language problem, but now we have like this two engineers problem. Like it's not necessarily like the same person that codes the algorithm and the model. And what we are doing is like, okay, now you can do all, yeah, but I don't know both of them. Like, but yes, it's okay, we can transition to that. And the result of that is I still have some bugs in my code that I need to solve. So there are some like successful optimization that basically hit the wall, but I will solve that. It's just like a question of time and prioritization. What we lack the most at the moment, but I've seen in the recent webinar that it's going to be really possible soon, is to have a streamlined way to put that on the hardware. Today, if we do that in C++ or Python, then we can just use ROS and push it to the hardware. I want that in Julia. I see it's coming. I'm super happy. Oh, I thought I would run out of time, but I'm actually good. So the conclusion is straightforward, but in terms of perspective, I put it small because I'm not so proud of it, but I have to solve my bugs. And all the animations you've seen are not in Julia, so I need to update that. But basically, I want to try transitioning to the dialed language for the model itself. I also think that the analysis on top of the part of the dialed language will bring a lot to the workflow. So that's something I really want to investigate and try that out, trying to get a license for it. I want to test, maybe I wrote it wrong, but I think for now it's the Julia C part for hill testing. Let's see if that's the best way to do it, but I'll talk with Ranjan. Then I want to expand to 3D plus planning. Everything you've seen here is 2D. As soon as you want to make like what the multi-term racks is, this machine here which is dancing in 3D, then you want that in 3D, like the path planning. You want to be able to make the 3D scan on the table, but you also have a bulking wall stand, I think it's called. Like, it's a wall basically that the patient can be standing so that the organs are like basically falling down naturally, and you want to basically make some imaging when the person is standing, and you want to move smoothly from one to the other, avoiding the table, avoiding the bulking wall stand. So basically, that's something I want to expand on. Last but not least, my colleague Marco is working on this semantic world, where we basically want to add some notion of what are the objects in the room, and try to add more basically discrimination around path that goes near, for example, patient or product like that could be dependent on the life of the patient, like the Irish, like the, what is called, like the breathing machine, for example. You don't want to hit that. But if you hit something like the door, it's less a problem, basically. So we basically want to go the green way and not the yellow way on this one. So that's something we want to implement. He has done that in C++. I want to have that in the path planning also here on Julia. Good, that's all.
Thank you so much. We have time for questions.
First of all, awesome presentation. I'm curious, you mentioned that you kind of use a static environment and then do an optimization. Have you looked into things like SLAM or whatnot, like simultaneous localization and mapping for dynamic environments as well, and incorporating it into this loop?
Yes, but not in Julia.
Oh, okay, interesting. Yeah.
we have done that, yeah. And actually the code is entirely running on the Aurora robot that you see.
I see.
And it's always like getting all the information from the radar, from the LiDAR, and just adapting and in the loop, always updating here.
Very cool. Did you, I'm curious, was there an attempt to try and do it in Julia, or is it just because it works as is and there's no need to?
Yeah, it's not yet there. It's like, that's as much time as could dedicate it to the topic,
Understood.
but I will progress toward that, yeah.
Very cool, yeah.
We have time for one more question.
Sorry, I should have let somebody closer ask a question. So in the initial simulation you had it following some trajectory, avoiding some obstacles. Presumably those are all completely static and it knew about those a priori, right? And then in your, yeah, so like that one, you just, or just go to the next one, the animation. I'm just thinking about the,
this one is dynamic,
blue, yeah, the blue things there. It's somehow been informed about all those blue lines in advance. In the almost the last slide, you showed some other potential obstacles. I'm just curious. Maybe you addressed this point. I'm not sure. is the idea that it would be dynamically constructing a view of the obstacles in the same way that, for example, self-driving cars are doing that, and then maneuvering around them?
Yeah.
Yeah, okay,
Yeah.
all right.
So once it runs on the, yeah, so yes. So basically we have both scenarios, so, and I would like to push for always like the simplest solution. So here it's basically an MRI room and it's like really, really clean. Everything is really, we know where everything is. Let's start with the map. Nothing will move. We'll have a sensor just to make sure that if nothing has changed, but we won't adapt the path unless there is a change. But for for example, the CAS lab or whatever, like I was showing with this Aurora program, then here we have like dynamic adaptation based on how the people move and how all the equipment is moved around. It's a nightmare here because like you want to have like this this type of mobile imagery C-arm that comes to make imaging when you do the operation, and they go out to basically give you more room to operate and then bring back to get another image, and the robot has to be aware of that and always seeing where these equipments are, and there are like cables on the floor, and you want to avoid that because you don't want to
Yeah, and
fall
I
over
suppose
them,
there's also the scenario where the robot's in the way of somebody, and it can't detect that it's in the way, right?
Yeah.
Somehow the person has to gesture or something to tell it to scoot over or
Yeah.
something, yeah.
Thanks. Yeah.
So let's thank our speaker again.
Thank you.
Oh, is it still not? Okay, cool. That's it. There we go. Okay.
So for our next talk, we have Zipline plus Julia, parting ways with our Julia simulation after 100 million miles. Let's welcome our speaker.
So yeah, despite the Zipline plus Julia here, unfortunately this is going to be a Zipline minus Julia talk. We have been using Julia for about 7 years, and we are no longer using Julia, so this is kind of a bummer of a talk, especially for me, because I am an active member of the Julia community, and I still enjoy Julia, but professionally, I have moved on a bit. First, I want to give a big thank you to Julia Hub, because when they first reached out about, kind of giving an update on what we've been doing for the last few years since the last time we gave a Julia talk, JuliaCon talk, we hadn't decided to move away from Julia, and I, accepted, and that was going to be great. And then, we got the news that we will not be using Julia anymore, and I reached out to them. They were like, you know what? That's really useful information for our community to have, and it's useful for us to grow, so go ahead and give the talk. So, kudos to Julia Hub. I thought that was a cool move, and I appreciate it just as a Julia user and community member, that's kind of the, attitude there. But yeah, so who am I? I am Johnny Diegelman. I am a controls and dynamics engineer at Zipline. We are a autonomous logistics company, mostly with flying things, but if ever in the future we wanted to have driving things, that could happen too. But yeah, our main focus is delivering things autonomously. On GitHub, you could find me either Johnny Die or Johnny Diegelman. Those are my two profile pictures you'll see also in different circles in Julia. I maintain and wrote some Julia packages, including component arrays, concrete structs, and simulation logs. I sometimes maintain them. I could do a better job. Thankfully, component arrays is now in the hands of SciML, so there are more people working on that one. And yeah, this was going to say something about being a father and have my family and everything, but as I was going through my phone, I saw this little flyer that my daughter made of my son, and I just decided to change this, and that's our dog, Mayhem, right there. So yeah, who is Zipline? I kind of briefly touched on it, but we do autonomous delivery of things. So we started in blood, medical supplies, vaccines, and stuff like that out of Cote d'Ivoire, Ghana, Japan, Kenya, Nigeria, Rwanda, and the US. We started in Rwanda. But yeah, so our first vehicle, this one's been flying since 2016, is a long range. That's like 80 kilometers out and then back, at least. I think it might be a little bit more, actually. Fixed wing, there's no landing gear or anything. We deliver via parachute. We take off with a launcher, and it's caught in the air, which you'll see in a second. Right here. It snatches out of the air. So this was all developed using Julia for a lot of engineering analysis and simulation and stuff for controls design. And it has taken us more than 100 million miles flown, which is a pretty far distance. And that has resulted, in some great things like 51% fewer deaths from postpartum hemorrhaging in the hospitals that we serve. So I think, despite the fact that this is kind of like a sad moving away from Julia talk, there's also like a really nice, Julia really did help us do some things that I think had pretty good impact in the world. Here's our Platform 2 vehicle. This is the one that I've mostly worked on because I've been with the company for 3 years, and so through most of the design of this vehicle. This one's shorter range. It's vertical takeoff and landing. It is a 2-vehicle vehicle. That little guy's called the Zip. It gets lowered for much more precise delivery than we could do with the parachute thing. It has much increased payload capacity, a lot lower infrastructure than the other one with charging stations and loading points. We are currently operating in Dallas-Fort Worth, Texas in the US as of a couple months ago. But yeah, the whole point of this vehicle is to kind of expand our capability of what we can do, in healthcare, reverse logistics if you need to take a sample back to the lab or something like that. Or, there's the food delivery use case or retail, all sorts of things. So this really helps us deliver directly to customers a lot easier, people at their houses and stuff. So yeah, I'll talk about kind of the brief history of Julia at Zipline. So back in 2019, Tucker McClure gave a talk called A New Breed of Vehicle Simulation. I'd encourage you to look it up. It's a great talk about our company using Julia. In 2021, we created what we call modeling.jl, which is our in-house model-based design and simulation framework. So we created that mostly for our new P2 vehicle as we were starting to bring it up. And then we created what's called Starling on top of that, which is our software in the loop, hardware in the loop, which I'll talk about this all in a second. And then now, unfortunately, we're chopping it off. So yeah, briefly, let me go into what modeling.jl is. So it's a hierarchical modeling framework. You think kind of like Simulink, but without the graphical user interface. It's all code, but it's still models can contain models inside of them, and data gets passed around by parent model between different child models and that kind of stuff. So in this example here, you might have a really simple world with an environment and a really simple aircraft in it. It's configurable. You could swap out that aircraft for something maybe similar. You could have a point mass kinematic aircraft if you only want to test certain parts of the software that don't care that much about physics. Every little part of the simulation can be configured. It's causal as opposed to like acausal, like modeling toolkit. So data flows one way, the way that you have to do in programming. Yeah, it's also continuous in discrete time. So models, there's a continuous side where they talk to the ODE solver and they give their derivatives, and then there's discrete stuff like software that doesn't have any continuous and only runs in discrete time. And then there's stuff in between. Actuators and sensors are like canonically the bridge between the discrete and continuous time worlds. So yeah, it could handle a bit of both. It's functional-ish to where none of the models are allowed to update their own states. They all have to pass out a named tuple that tells how to update the state derivatives and all the children to the framework. This is really helpful for things like basically you could get into a lot of trouble with ODE solvers if you allow your models to update their own states or state derivatives, because that breaks a lot of the assumptions that ODE solvers have. So this prevents that. And it's models all the way down. Everything in it is a model. Everything we do is a model. Models can initialize with an init function. They could do continuous dynamics, which basically FC function tells the solver how to take time derivatives, and then FD for any time you need to do an instantaneous update of some variable, whether it's a discrete variable or continuous. So Starling is built on top of modeling.jl. In this picture, that little wood there, I guess, is modeling.jl, and the Starling is on top of it. I didn't really think of the metaphor very well. But so it's a software in the loop that runs either synchronously or asynchronously in real time, and also has a hardware in the loop mode. For us, what that means, hardware in the loop, is like you're actually running on your flight target, like on your flight computer that you would be running in real life. It could also mean that you have actuators hooked up and stuff like that. There's like a whole range of what hardware in the loop could mean. But yeah, so all of the process launching and everything, orchestration, it just happens through the models in here. And what we're talking about in scale, it's like about, yeah, like over 60 external processes that it's talking to, and then like a lot of processes, like 25, that it's like mocking internally in Julia. So there's quite a few processes, and then there's, I'd say, like 300 something continuous states that we're integrating. So that's about the scale that we're doing here. So yeah, I guess the main point of the talk is like, what challenges did we face in Julia, and like, why did we ultimately make the decision to move away from Julia after using it successfully for quite a long time? Before that, or one of the challenges is kind of not necessarily Julia based, but like really plays into this, is there's kind of two cultures of engineering simulation that I think that we don't always think about too much, but like, one is the physics focus, which I think probably a lot of the people in this room are going to be more on this side, where to you a simulation means solving a differential equation, and anything else is like extra on top of that. Whereas the software focus, if you're writing flight software or robotic software, and like that's your main focus, simulation really means like stepping algorithms forward in time, kind of. And then physics is just like another algorithm that you're stepping, kind of. Whereas in the physics side, flight software is just like another model in your solver. So in the physics one, the ODE solver controls time. In the software one, the orchestrator discretely steps time. Why this matters is, in the physics-focused one, the continuous states across different models, they can sub-step together, and that really matters for how like solvers work. Like, you can't really have the same modular physics if everything just has its own step function, because if you take like the old RK4 method or something, it's doing multiple sub-steps per continuous step. And if you can only step time discretely, you have no way of actually communicating across sub-steps. So the physics-focused version can handle more, but it's also a lot more clunky and kind of like difficult to use, which is why like when possible, like the software focused is like kind of an easier way to go. So a lot of different types of robotics applications and stuff might focus more on the software focused side because you can actually make a much easier to plug into simulation. So one of the big problems we had with Julia specifically is basically all of our flight software and everything depends on Julia because Julia simulations gate all of our flight software from getting through CI. Like basically, you want to merge something that's going to get run on the vehicle, like it needs to run through hundreds of different tests and validation suites that are running full simulations to make sure that the behavior is correctly. And so Julia is this little thing, and it is maintained by a small handful of people, and then like hundreds of people are writing the other code that depends on it. So when something like breaks in CI or something like that, it's usually, you know, there's a small handful of people, if it was in the simulation, that can actually fix it, and everyone is kind of waiting for them. So another problem we kind of hit is, you know, type instability is always a thing, but, you know, there's a lot of things that it breaks in our specific workflow. But you kind of have this cycle where it's like, okay, you don't want it to break, so the way that you prevent things from breaking is you put in regression checks and make sure you can't write more type stable code, but you can't do that until you get your code type stable. So you spend a good amount of time trying to fix all the type instability, but you know, if there's one or two people in the company that are proficient enough in Julia to do that, then it takes quite a bit of time. And in that time, new type unstable code is merged, and you didn't get in the regression test to fix it, and you're back in the loop. So this was a loop that we had a really hard time breaking out of, and I would encourage anyone in here, if you're taking on like a similarly scoped problem, deal with type instability first, put in regression tests first, and then build on top of it. It's definitely not something that you want to come in and clean up later. It's a, you know, there's no such thing as premature optimization when it comes to like type instability. Like it's always the correct way to go. Another issue we kind of had is JIT compilation. You know, modern build systems like to, you know, they want to run a bunch of tests in parallel, and they just want you to like tell them what to compile first, and then it's going to distribute that across all that. But you know, JIT compiled languages don't play super nicely with that workflow. Yes, you can run a warm-up run, and you could like cache the compilation results. But if your simulation is extremely configurable and each different configuration of the simulation is like an actual different type, which maybe that was also a mistake, but you know, that really can cause some challenges here. So like this is where type instability and JIT compilation like kind of come up in real life. So this is a plot from like our real-time sim, like running in hardware in the loop, where if we fall behind real time too much, like the vehicle in simulation will like just fall out of the air. So this is something that we saw that we were running 2 full mission warm-up runs before we ran this real-time sim, and we would still hit, what we actually saw was JIT compilation in the middle of the sim, because we had type instability and we were going down a code path that maybe the other ones possibly weren't or something, so you would still have to hit JIT compilation despite the fact that you did a lot of other warm-ups. So yes, JIT compilation like plus type instability is like especially bad things. So yeah, what are we using instead of Julia? So a brief aside, there's a thing called carcinization, where, you know, nature tends to like to evolve things into crabs. What does this have to do with software? Well, there's a software version of carcinization, which is the tendency of programmers to want to rewrite things in Rust. And if you've ever met someone that uses Rust, you probably know this type of person. But it's because they really love writing Rust. And I've, you know, been using it for a while too, and like I get where they're coming from, especially around the tooling. And, you know, this joke works because their mascot is a little crab named Ferris. So, yeah, what this looks like for us is this kind of like Ouroboros thing, except for the snake is eating other languages' tails, which I guess is just cannibalization. So, like, why do people love writing Rust? Like, on the surface, I wouldn't have expected Rust to be a language that people love. It's kind of like, if you were to say, you know, writing concurrent programs is difficult, what if we wrote a language that made serial programs as difficult to write as concurrent programs? That's kind of like the pitch of Rust, and it sounds like it wouldn't work at all. But the tooling around it is so good that most people don't actually complain about it because mostly the compile time errors that it can get are really nice. So for example, we have this function here, and I want to just add an extra input that it's not expecting. What does the errors look like? So we see right here we get two different errors. One of them says, okay, you tried to access some foo value from inputs. That's not one of the available fields. So here's a nice little thing that tells you exactly what is available there. And then you get another error right below it that all ran at once that tells you, hey, this function expected 3 arguments, you gave it 4. It's very clean, very easy to just find exactly what went wrong. It points to what went wrong. You could even say cargo fix, and it will fix some of these things automatically for you. It's really cool. And what's really neat is when you're working on a big project, you will go to compile something, and you'll get all of your errors just at once, and you could just go through and fix them. You don't have to do the cycle of run my code, hit an error, run my code, hit an error, fix, run, and go back and forth. Especially when you have JIT compilation, that means, you might be hitting that error a couple minutes into your simulation or something, and that could take a long time. So it's a really long development cycle there. So this kind of fixes that by catching it all at once. What's my time, by the way? I don't. Okay, cool. Good, I have some time to talk about some of the other cool stuff. And some of this stuff actually we can have right now in Julia, and I think it fixes some problems that are nice. So I talked about before this case of you have these different simulation configurations where every one of them is a completely different type because they're parameterized by different types. So Rust enums kind of fix this problem, and we have this in Julia. It's either sum types or Moshi. There's a few different packages that implement these sum types. And the idea here is that let's say you want, you have that situation, or you have a bunch of different types and you want to make an array of all these different types. That would normally be bad in Julia because it would be abstractly typed, right? You can't hold a bunch of different types in an array and expect, fast, a fast program. But with this, everything is one type that just gets represented as one type that with 3 different variants. And then you could have a match statement that you could kind of ergonomically go through and hit stuff. The downside here is it's basically as if you're doing an if statement where someone else can't buy into your, they can't write a method for this if you're going this route or whatever. You can't add on a new vehicle type or something. So there are some downsides as opposed to, abstract types or whatever, super types. But it's really nice if you're the end user writer of the simulation and you know all of your variants and you control all those. We could have this right now, almost the exact same syntax in Julia too. We do have this. Traits are really nice in Rust. Another reason people like it is it defines exactly what will be implemented, and this actually is what helps the compiler know whether certain types have certain methods implemented or not. So you know, we might have a trait that's like number of doors, and we want to implement that for vehicles and houses. And the cool thing about this is if you're setting a function signature or something and you only want to allow like a type that implements number of doors, like it will strictly enforce that. And yeah, it's a really nice thing. And if you've ever like worked in Julia with like interfaces like iterator interface or like broadcast interface, or if you written your own array package like I have, like there's a lot to be desired in knowing how to implement interfaces in Julia. Like I've had some struggles with it, and I think other people have too. So it would be cool to have like really like nailed down, this is what your interface looks like. But you know, it's not all like one way. Julia actually has like a lot of really cool stuff that Rust doesn't, that, you know, definitely like I'm missing when I go to Rust. So like I think it's worth like at least pointing that out. SciML ecosystem obviously is great. Package composability is like another huge one. Rust has the same type parameterization, but it's more like a cultural thing. Like in Julia, like our culture is to always want to be composable, and like languages kind of, other languages don't have that. Better prototyping experience, and then, you know, like a little type instability is a treat sometimes, because if you want to set up your configuration of your vehicle from like a JSON file or something like that all needs to be done at runtime. Really hard to do like in a compiled language, but if you could have a little bit of type instability in your initialization of the simulation where performance doesn't matter, you will build a concretely typed thing that can run through the loops really fast. And that's like a really cool kind of like superpower of Julia that I don't think gets talked about enough. So yeah, that's kind of the end of what I had. I hope to have a good amount of time for questions.
Okay, so we have a lot of time for questions. Let me start. I don't know who raised their hand first.
Do you miss multiple dispatch?
Let's see. I think you kind of like end up using it, at least I kind of end up using it less than I thought. Or like sometimes you kind of overuse at least I tend to do it. I overuse multiple dispatch in cases where it's like I would have been fine to like not even be polymorphic and just like write a separate function for things. But I use multiple dispatch just because, you know, it looks, you know, whatever the way it does. I do kind of miss it just because I've been using Julia for long enough that my brain just kind of thinks in multiple dispatch ways, but like I've also tried to like sell it on other people that like use Rust, and a lot of times they don't see like how it's nice until you give like an example of, you know, like adding two matrices or something like that. But like I think those use cases are also like a little bit more like rare in the type of code that we write.
Thank you. This might be a two-part question, but they're related. You mentioned the dependence on just one or two people who know the GNC Julia library as an issue. Could that also be seen as a benefit where because of Julia's high-level expressiveness, one or two people was enough? And how many people do you think it will take to support a Rust implementation? And the second part, if I may, is have you tried recruiting additional Julia developers to expand that team? And how did that work out?
Yeah, no, that's a great question. It's actually one that I wanted to bring up, but I kind of forgot to hit on it. So one of the things I forgot to mention is our entire flight software stack, for the most part, is written in Rust. So we just have this like incredible like depth of like knowledge in Rust to where we can always lean on those people. Like if you're writing the simulation, we just don't have that in Julia. Yeah, and then the second point is like hiring for Julia. One of the things that like we want to make sure of when we're hiring people is that like we really want to make sure that we get people that like are really good at like, their domain knowledge and good at solving problems and thinking through stuff like that. And like kind of at the lower end of the list is whether people are good at certain software or programming languages and stuff like that. Because at least to us, like that stuff can be learned faster than, the engineering skills that take a lot longer to build up. Like most people that use Julia in our company, like we don't hire anyone for the most part that I know that, except for me, that like had Julia experience before the company, but like the ones that use it like got up to speed pretty quickly. They're just not able to like dive into the deep parts of, fixing, type instabilities and stuff without more experience. So, yeah.
Yep. So I was wondering if you could speak a little bit more about, like what are you, for this way that the programming is being used, right? It's being used for this use case that's real time, embedded, and whatnot. Like, what are you giving up when you go down this decision to Rust, right? I mean, because I think that it's pretty clear. Like, okay, you have a software engineering division, and they're the ones that got to maintain code, and they're like, oh, of course, the locking it down makes it easier to maintain. So there's a lot of pros there. I could see where that could come from, but I mean, you're the controls engineer, though, right? So what are the certain things that like, are you able to still do all of the controls analysis, or are you now you're kind of saying, oh yeah, now we don't do this as controls analysis or whatnot. We might have a little bit less controller efficiency, because there's a trade-off in here. So could you describe what happens with this trade-off in terms of like how physical you get and how physical you're now able to do, and how that kind of interacts with the realization of that in the true product?
Yeah, that's a great question. So the part where that stuff is like the most useful is in like the earliest days of like developing the vehicle, and like if you're constantly just changing what your vehicle is looking like that's where it's like really important to have the most easy to use like iterate on tool, which I think Julia is a little better for. When you're a little bit, like your vehicle's a little more mature, you start to lean more on like the software style of thing. With that said, we're still doing a lot of active development work and controls development work, and we always will be. And it is, yeah, like that is a huge thing missing in the Rust community. What we do is we'll still use Julia, or some people are using MATLAB. It's kind of like, grab bag for different teams and stuff like that, or Python for doing like a very specific analysis, but like that analysis won't be necessarily something that plugs into our main sim. Like if you're doing a linear controls analysis, you're kind of like building up your linearized thing from there, if you're not like linearizing it in the model, which we had in Julia, which is kind of sad to leave behind. But yeah, there is a lot you're giving up on that side, and that was like very clearly going into this one of the trade-offs we were going to have to make. But just given that we have so much of the company that like relies on this infrastructure that needs to land on Julia, that it ended up being the right trade, I think, there. So it's a little bit harder for a small group of us like me.
So I might be a few years out of date asking this, but when I last checked, and this was a blocker for me using Rust, a lot of the numerical stuff that like ages ago was in Fortran and people have written in C. I'm thinking about ODE solving. I'm thinking about like finite element stuff. It didn't exist at all in Rust, at least a few years ago, and like in really and there were some like packages that were kind of kludging on the Fortran stuff, and so you lost all of the benefits of Rust.
Mm-hmm.
Is that still the case, or is does that ecosystem, like you had it on your slide, no SciML ecosystem. Is that better now, or is it something you're doing in-house, or
It's
you
a
don't
little
need
bit.
it?
Yeah, we're doing it in-house, our ODE solving. Just mostly because we don't have that. We do have a lot of requirements. We do have like a finite element tether, but like we're kind of doing stuff to work around that. But yeah, There are a couple ODE solving like packages in Rust, but they're very bare bones, you know, like give it a vector, and there's not like a lot of like, you know, callback, or there's like a output grabbing callback and stuff like that. But it's not to the point where you were saying where it's like calling into Fortran. At least like most of them are written in pure Rust, so it's nice for that. But you're not going to get like hundreds of different solvers and have a whole callback ecosystem and all that kind of stuff.
I'm just curious what the plans for, you know, Starling and modeling.jl and so on are in terms of, you know, will they be open source, or are there, you know, sort of an open?
Yeah, that's a great question. Certainly we couldn't do Starling because that has like a lot of our specific, you know, flight stuff, but modeling.jl purposely was kept aside in the intention that maybe one day we would open source it, and I think a lot of people are amenable to that. I don't think we would want to invest any time in maintaining it, but like possibly I could just get it under my own name and do that, and I wouldn't mind doing that at all. So yeah, that's a great question. I don't know.
So let's thank Joni. So we are setting up for our next speaker on Julia-powered BI engine.
Is this yours? Oh.
By Matthew.
Yeah. Let's see if it'll work. Huh? Yeah. Just to make sure I got enough power. Okay, so once we run.
The floor is yours.
Okay, well, hello, and thank you guys for letting me be here. I see we got all the cool kids in the room, so that's pretty good. So I'm Matt Myers. I work with a group called PlanView, and we've been working on building a BI engine in Julia, and the goal is to basically be able to get away from the current technology that we have and move off into something that's more cloud-based or more distributable. And so what I wanted to show you today is what we've built and kind of where we're going with this. So in this presentation, I wanted to kind of delve into some of the aspects that we have here, what we've done, kind of give you a little bit of the target audience for people that might be actually interested in this. Some of the key takeaways that we're going to try to shoot for here is try to understand the benefits of the framework and how we do this manipulation and analysis in Julia. This new technology that we brought up that I refer to as chained formulas, how we do the caching and the programming and how Oxygen plays into that. And then we're going to try to show off some of the insights that we've gained and the challenges that we've run into during this project, which has been roughly 2 years in the making, and then we'll talk a little bit about how this is actually making the PlanView Advisor product better. And then so quickly, I just kind of want to show you guys what we're doing here. So this is kind of what we're trying to generate, right? So this is what the PlanView product generates. It's a simulation type software for BI, portfolio analysis. We primarily focus on, life science, pharma, medical devices, but we also do things like oil and gas and stuff like that. So it's not specific to any particular vertical. It's really based on the skill set of your modelers determine the capability of the application. And so here's an example of some of the graphs and stuff that we make. You know, the example like simulation, a lot of people see this. And we do this in a way that allows this types of simulations to be flexible, so you can change the type of simulation or the bounds and a lot of things like that. But that's not really the main point of the talk, but I just wanted to show you some of this. This is kind of the big picture of kind of what we do and kind of what we're doing with Julia. Okay, so you can see here a lot of stuff on this slide, a lot of eye candy here. There's a lot of areas that we deal with, and I want to just say types of different simulations. You can see we do Monte Carlo, we do the median Latin hypercube. So there's a lot of things that our customers want. And so what we're doing is we're trying to move into a world where we can just make it run faster, right? Faster and better, and scale it and deploy it. And so this is kind of our physical architecture of what the Advisor product looks like. And you can see over here that we do have the Julia piece kind of in spot here. So this is where Julia Hub comes in, right? So we have this big architecture with all this stuff, and then it's like, oh, by the way, let's bolt on Julia and see if we can make this thing run better. And so the project here, the Jade project is what we call it, is basically we're trying to create a high-performance engine. This is developed primarily in C#. The actual Julia engine is in C#. And then the Jade piece is actually pure Julia. Okay, and so the Julia engine is really a math formula translator. It reads, I'm not gonna say all of them, definitely not, but it reads several third-party languages and some standard shorthand languages that are out there, and I'll show you some of that. And so the deal here is that we have the C# engine that manages all the formulas, controls some internal caches. It's the gateway or overarching piece for the entire, I want to say transformation engine or decision engine. Jade, which we're just lovingly calling, you know, just another decision engine, right? No big deal, right? But this is actually a bunch of modules, not a lot, maybe less than a dozen, and it's used to actually drive all the formula chains. So we create all these chains and all these variables and push them into a model that is built programmatically, right? And so we go from a representative model into a programming model, and then that is loaded up into Julia. And some of the core pieces of our framework, we have this notion of it's basically like these 4 pieces. There we have an ND table or an n-dimensional table, which is really multi-dimensional arrays that have intelligent indexes. So instead of just being a standard matrix, you have a matrix where every dimension of that matrix has a well-defined index that's bound to it. And we use that to allow ourselves to better flip and spin and slice and subset the matrix. And then we have things that are known as like an index. Kind of makes sense, a discrete value of ranges. We have this notion of a choice, which is like a list of things you can choose. And then, of course, we have the smallest thing, which is a scalar. And the idea here is that we break everything down to a set of these 4 objects. And then from these 4 objects, you can do any kind of math that you want. So that means you can take like an ND table and add a scalar. And when you do like add or multiply, it knows what you're talking about, right? It knows that means that you're going to add that scalar value across the entire matrix. Okay, now if you said, well, I have something like an index. Well, can I add indexes together? Of course. Can I multiply them? Of course. But could I add an index to a table? And what does that mean to multiply an index to a table? So we've worked this out into a structural language that allows you to then do fairly simple formulas that do very dramatic data manipulation. And so this is kind of an example of some of the structures. As you can see, it's pretty simple, right? I mean, as far as for tracking and what you really have in here, we try to keep it as simple as possible from a structural point of view. You can see all these are mutatable, so that we do things like where we inline mutate structures that are the result of a formula. And so the framework is basically set up where we have dictionaries of formulas and dictionaries of structures, and the formulas produce structures, and the structures are habitually used for doing your actual math calculations or the formula calculations. And then this is what the Julia engine looks like. We can see here we start with a BI model, a business intelligence model, that basically is the representation of all the math and the formulas and the outputs that you want to generate. It contains things like tables that would be static that a user might manipulate or enter or change. And it also contains simulation or stochastical formulas for generating any kind of output that a client would want. Okay, so this basically comes through, and is turned into a bunch of chains that are then fed into this model manager. And all this is written in C that you pretty much see, this is all written in C#. Okay, so in this model manager basically reads these text files in, and you can write it in a number of ways. It could be like an INI file, you could write it as straight text files, it could be MATLAB type formulas or Python formulas and stuff like that. And so, and different people use different interfaces to do it. You can use a UML type interface, it generates a text file. It could be a spreadsheet that generated all the formulas. It really wouldn't matter. Okay, so then this basically brings them all in, and we have something that we consider as what's called a block parser. And the block parser will take the discrete chunks that describe what the formula is, things like the name, give you a name, a title, some information, and then the actual formula definition itself. And that formula definition can contain anything from standard math formulas to things like references to the other variables. So you can have, variable A plus variable B, right? And in this case, it might be something like all regions is reduced down to a matrix of data that has trials or samples or medical information. Okay, so this model is actually a bona fide object. So it basically comes into existence from reading from this block parser. And then it generates a formula graph or a graph model of all the formulas and their associations, right? So it creates a full hierarchy of upstream and downstream associations and binds everybody together so we can understand what might change and what needs to be recalculated. Okay? And then from here, this model manager actually turns it into a model graph, okay, which is a little different than the formula graph. So the model graph is a bigger, more robust representation of all of the business logic. Okay, and so from here, we now have everything that we need in order to start processing. Okay, so all this is fed into the Julia engine. Once again, this is also C#. And this Julia engine then has a lexer and a parser. Now this is actually external. Okay, so this is some of the magic that I wrote here. So this lexer will create a lexicon of the language or the formulas that you're looking at. And then the parser will translate that lexicon into Julia. Okay, so then the idea here is that if you want to support other languages, you only have to adjust the left-hand side, right? You can make a different lexer, or you can make the lexer smarter, and then the parser will understand how to create all the Julia code that you need. And the code that it creates is specific to the PlanView functions library that we've generated, and I'll kind of show you what that means. So then this lexer reads in the formulas from a third party, generates the JL code, and then that then comes out and we feed it into a cache. So the idea here is we don't want to redo the work over and over. So every piece of work that we do, we end up saving it off to the side. So we're using a manufacturing approach to building the actual BI system. So as all these pieces flow through, they get chunked together into smaller components and then larger components to where we can do basically a just-in-time engine creation. Okay? And so from here, this engine will then take all these subcomponents that it's built, and then it will actually run it out and create what is known as the engine data. Now, engine data is basically the thousands of formulas all put together into a Julia language structure that primarily consist of nested functions. Functions that define data, functions that define the object. And then this separation allows the functions to be reinterpreted at real time when the underlying components change. And then this Jade engine has its own internal state cache. And this allows us to store the current state of the engine so that we can come back and reset to a point in time. Now this is useful for what you hear a lot of people talk about is this pre-compile problem and this just-in-time problem. So what we're trying to do is we're trying to get away from all that. So this way we can pre-train the engine and then also post-train the engine so that when it's running, it'll get follow-on training that is the real-world math that it needs to do. And then by doing that, we can save it all into a state and restore that state. And then we get about 10 times the performance of our initial run. And then by doing this, we can create these engines in the background, set them up, get them going, and then we have a really fast turn on it. And the state in between these two, there's a process state that is linked in between these two so that the engine knows what the story is of the JADE computation piece. And then oxygen is used up here is the main interface. So we have an internal linkage, there's like a process level linkage, and then we have this external linkage. And the external linkage is basically API calls, REST calls. And so this engine is actually freestanding. Once it's up and running, it really doesn't need necessarily the rest of the architecture. Like you can connect to it through another API setup. You can use a web interface, and and in theory, you could make and create and do stuff. You could even do it through like curl commands or something like that, or webget. Okay, and so then here, this Julia engine, this is the interface to the Plan View Advisor software, and this is the piece that I was kind of showing you some of those graphs. And so this will basically do all the calls, and these are the BI service calls. So the application says, hey, I need to do something. It comes to the engine looks to see, have I already done that? Do I already know what you're talking about? If I do, I'll just give it right back to you because I don't even need to go down this path, okay? But if the engine goes, you've made something dirty, you've changed some data, you've changed the table, the user has adjusted something, and I don't think I have the right stuff. So I'll communicate over to here, tell this engine to do the work that I need it to do, pull the data back over, and then I'll store it again. And then I also will communicate back through Oxygen any kind of hierarchical or dependency changes that the engine believes happened that Jade doesn't know about. Okay, so Jade is savvy enough to figure out a significant amount of the hierarchy and maintain upstream, downstream relationships, but not necessarily if there's some kind of low-level or complex change that the engine does, because a lot of this can happen dynamically. We have something that the engine does is called node farming, where it will generate thousands of variables on top of the thousands of variables that are already in here. So the system will come up with a default set of data or a default set of formulas, and then based on the processing and what we need to do, we'll create more of these variable farms or node farms to do follow-on processing based on what the user is attempting to do. So that could be things like complex waterfall, tornadoes, unwinds. We might need to make more stuff, and so we'll make it on the fly and then synchronize between these two. And then, of course, if there's a change in the graph state because of the model changing, then we have a link here where the graph state is maintained between these two objects. Okay. And so that's kind of a lot. Okay, so, and then kind of getting into what the engine is. So the engine is basically designed to, this Julia engine is designed as a code generator, right? And so it will produce the code that creates the Jade piece. And then Jade is designed to run both locally or on hub. So you have a manufacturing process that creates all the libraries, it creates all the function routines, it generates all the code, and then it pre-compiles it, it exercises it, and then it stores it. And then from there, we're able to create both local packages or sys images on Julia Hub in order to control how we really want to use the capabilities, right? And so here we talked a little bit about there's this manufacturing approach where you build once and assemble many, and this allows us to then bring systems up or the different components up very fast. We have this notion of state capture that I kind of talked about on the state piece, and that allows us to store the state of the current engine so that we can then reset it. And the reset ability is one of the key technologies that we have here, because it allows you to keep a fully pre-compiled hot instance of Julia that is ready to go. And this will, like, it increases performance either 1 or 2 orders of magnitude from a kind of a dry run where you have to have intermediate compilation. We support a hybrid approach where you can run this locally and remote at the same time. So the Advisor product runs a certain set of operations locally for expediency and latency control, and then the background processes that run for background data set recompilation, data ingestion, and things like that, data imports that require an engine to recalculate data or to normalize data, then it'll run in the background, and those background processes will be fired up on Hub. And then this allows us to scale large data loads out onto Hub and then have fast responsive engines for user interactions. So when there's a user behind the process, we want it to just be as fast as possible. And if the user isn't there, we kind of don't really care. It can take a little bit longer, and you can put it in the background. One of the big differences with this setup is that we are a high-frequency interaction, high-frequency change system. So maybe a lot of the Julia things that are done are more of the fire it off and go to lunch and come back and get your simulation results. In our world, the users don't want to wait on that. They don't want to do any of that. They want everything to be as fast as possible, so they don't care if it's a week's worth of work. They still want it within a few seconds or a minute, right? And so that's kind of one of our big things here is the frequency change. We do support several third-party languages. The Lexer is designed to read both formulaic and shorthand, and it produces Julia code. The parser then produces the Julia code, and I'll show a few examples of that. Locally, we use compiled modules, right, where we build a module, and then we pre-compile it and store it as a package, and then reference it at a package level. On the Hub, then obviously we make system images, and we manage those. And we found out that, yes, if you have your manifest with specific libraries and stuff that you're using, and you have your code, the system image will include your code. Okay, now, maybe that's not something that everybody understands or believes, but it is an important thing. Okay, so that means you cannot have one manifest and multiple code bases at the same time, where I have my function library, and then I have a set of libraries I depend on that's in the manifest. If I change my code, that system image needs to be updated because that code will be in that system image. Okay, so what we do is we have changed things to where that engine data that I talked about, that might be 25,000 or 50,000 lines, it's not part of the system image. It's held as a side piece that's included real time. And then this lets us do training on all the functions and routines that go into the system image for the performance gain, but avoids pollution of the system image with the engine data that may be from different models. Okay, so the Advisor product tends to have multiple models that run at the same time, and those models interact with each other. And so because of that, we pull the model data out and leave it on the side. And then we dynamically load it at runtime once the image comes up. And we do a lot of workload training to improve performance. We do both pre-training at the pre-compile time, and then we also do runtime training when the system is actually up and going. Some of the benefits that we've run into, some of our benefits and challenges here, it is a very flexible framework for sure. It supports a lot of extendable features. You can just keep kind of adding on to it, whatever you want. Somebody comes up with something new, they can just kind of plug it into the library, and then you can just start using it, just using it. The chain formulas, they smartly recalculate. It has this whole hierarchy tree, and everyone knows their dependency. And so therefore, everybody knows who's dirty and who's clean. And then we only recalculate the dirty nodes or the dirty variables. And then that allows for lightning fast calculations. And then because as you go farther down the calculation stream, it becomes more complex. And that endpoint tends to be what the user wants, which might be a summary, a graph, some kind of data. Okay, and like we said, we support the high-speed changes and high-speed recalculations. And it supports dynamic workflow. Okay, so this is where I was talking about you can dynamically alter the model real time based on programmatic needs. And so therefore, if you want to do a set of calculations that require formulas that are not in existence, you can have the system dynamically create all those formulas and create all those associations, and the system will naturally understand where those fit in the overarching hierarchy. And then they will smartly participate and recalculate. Some of the challenges that we ran into is obviously third-party languages. Creating a Lexer that will take apart a third-party language and create a lexicon that you can then run through a parser is fairly difficult. And so I'm the one that wrote that, and I will attest to the fact that it is fairly hard. Even with AI support, AI kind of sends you astray sometimes on those. And then one of the big things was learning what makes Julia happy, right? I mean, I think we all might struggle with that, right? What is it that makes the language happy and performant for you? So that was a little bit of a learning curve, and we definitely thank the Julia Hub guys in advance on that one here. They have helped a lot for us figuring this out. So we didn't have to do this, we didn't have to do all of this on our own. We actually had some help ramping us up. Debugging, I think a lot of people know that debugging a running process can be difficult. Some of these engines will have 1,500 variables. Some of them will have 4,500 variables or 4,500 formulas that are all chained together. And our system is eventually consistent, so it's also self-healing. And so that means that as it runs, even if it had an error, it might self-correct that error and then keep going. But that's not always the best thing because it's hard to figure out what the bug or the problem was or the crash point because it didn't stop the system. The system doesn't just stop and crash because there was an error or a problem. It keeps going, whether you like it or not. And so we wrote a way to record and replay all the activities of the engine. And so this lets us then run a set of scenarios, and then if we run into a problem or a bug, we can record the situation, you can pull it off onto the side, you can give it to your other team, they can run a replay that back to the crash point, and then they can look and go, oh, I can see exactly what went wrong, I made a mistake, or I didn't understand something, or I have a signature that's wrong. The other big thing was package creation, right? How do you do all these packages, and how do you create them and manage them when you're doing all this programmatically? All these are being created on the fly, and if you want to stack these on a server, how do you keep them from conflicting with each other, and how do you keep yourself from basically breaking another running instance if you have common packages that are running on the server? And so this was a lot of the big things that we had to address. And so here I wanted to show off a couple code examples. This is one that my cohort Chase wrote. And so this is basically what we call a remap. And so we deal with a lot of flat data. And so we have this notion of flat files and flat data, right, which is very much like a sparse array, right? So the deal is, you know, do you really want to unwind all these to look at them? Let's say you have flattened data, but it's a matrix that might be 5 dimensions, but it's been flattened down. And then you only have the data that's changed in this flattened dictionary or this flattened set. And typically you blow it up or you unwind it, right, into the full set or the full matrix before you typically operate on it, right? Because if you have a flat data set, it's really hard to do matrix operations because it's not a matrix, right? It's totally not a matrix yet. But if you unwind it or inflate it, then it becomes a matrix. So what we've done is we've created this remap notion where you can remap the locations of a matrix down to its flattened components without unwinding the whole thing, and therefore you avoid creating intermediate matrices that may be like hundreds of millions of cells, when really there might be only hundreds of thousands of pieces of data. And so this allows us to then do this. This is like our unflattened loop. This is chunks of code buried inside of chunks of code, right? But this is an example of where we would be remapping a coordinates that was coming in as we were unflattening the data. And so this lets us go through and do operations without fully inflating the data. This is an example of some formula transformations, right? You can see some of this is pretty simple, right? You know, we support basic structured languages, and you could say, well, Matt, you know, that doesn't even really need to be translated, right? I mean, Julia will probably do that, right? But that's not necessarily always true because the people that write this stuff, they don't know Julia, they don't follow syntax, they just know some basic formula creation methodologies, and then they know things like this shorthand, okay? So here you can see where one of the things we ran into is scope, right? When you do this, there is scoping issues. And so if you don't localize a lot of these things, you'll get scope bleed, and then your functions will be all over the place. This is an example of shorthand. Maybe some people recognize this from Python and MATLAB or some other things. But this is an example where the parser will take this apart, or the lexer takes this apart, and then the parser will produce this. And we can see this is our ND table here, and then we can see that this is basically the formula that would be generated. As a very small example, this would be like one formula that would be generated. Here's another example of a variable, like this is our bi-quarters year type formula, and we can see that this uses something that's called a vectorizer that basically has the ability to read through arrays of formulas and know the difference between arrays of formulas or arrays that might have dimensional data in it, and then it can inflate the top level table. So let's say you have a one-dimensional table, but every entry in that table is 2 dimensions. The vectorizer goes, oh, I understand what you mean. Let me turn that into a 2D table, and I'll bring the indexes from the lower level up to the higher level, and we'll normalize the whole thing back out. And so this is an example of what it makes in order to make like one simple variable. And then here is an example of something very similar, only this one is like a choice. And so here we can see where we have this notion of the data piece that's being created, the actual index piece that's being created, and then we have this notion here as we run, are we going to dynamically build this or not? If it's already built, then we'll skip it, and then this is considered a piece of static data. And static data can be externalized so that we can fast load it into the system so you don't have to go back through the formula building process. And then this is an example of a larger formula, right? This is a more robust example of a fairly reasonable size formula. And so you could have thousands of these that chain together, and the main way they chain together is this little guy right here, this get var. As you notice, we do this thinking like get a variable is what that really means. And then the variable has a name. And then this one will have a formula in it. This represents either a formula or a structure. And then based on where the computation, the calculation happened, these are either already calculated or not. And we can see that these take standard structures, name structures, right? And then we basically created an overload map that overloads all the Julia operands. So we basically have overloaded all the operands so that they understand how to work with our native syntax and our functions. And then this is kind of some of our stats here. So you can see some of the modules that we used and then some of the code lines that we've generated. We can see that we generate about 20 to 50,000 lines of code. The actual routines that we built for plan view functions runs about 10,000 lines. We have about 1,000 lines in Oxygen. And the engine is about 5,000 lines. So you can see it's not that big until you get down to the code generation piece. And then kind of with that, I will definitely say thank you to my coworkers, Ohad and Chase, and thank you to the Julia Hub guys, Phil, Matt, and Luke. And I think with that, I don't think, are we out of time? Yeah, okay. I can take.
Thank you so much. Matt, I think I'll take one question because then we'll go to our last talk of the session. One question.
So just curious with the Jade engine. So some of these formulae that you displayed there, do they have to, I mean, can they change dynamically over time as well?
Yes, absolutely, absolutely. And so as this runs, I'll just show you. This is an example of the engine running formulas. So this is the output that is generated when we run and calculate things. And just as a quick thing, I know we're out of time, but you can see the graph comes up, right? And you can see this is the running engine. We change to another piece. You can actually see the engine recalculate different formulas. And if we go to something a little bit deeper, under the analysis, maybe a tornado, you can see all the formulas chain recalculating there on the screen. And so as it does that, it goes faster. And so as the system runs, these formulas may change on the fly. And so that's why we maintain the hierarchy and the dirtiness factor. So we only recalculate formulas that have actually changed or have an impact on them.
Okay, thank you so much
Thank
for
you
the
all.
awesome talk. And as our last speaker of the day in this room, we have another Matt. And let's just give a minute while they set up.
Okay, all right, appreciate it.
Okay, so let's welcome our speaker. We'll be talking about a prototype to production pipeline with Julia.
All right, thank you. I appreciate the opportunity to be here today and talk with you. So my name is Matt Adams. This time last week I worked for ANSYS, now I work for Synopsys. If you were at the keynote by Prith Banerjee earlier this morning, you know that we had the merger with Synopsys. So what I'll be talking about today is the work we're doing with Julia and the ANSYS Twin AI product, but that's now part of Synopsys. And this will be in some ways a continuation of Prith's keynote talk this morning, and hopefully give a little bit more context at a lower level of why we're interested in looking at Julia here. So I was going to say I'll start at the 30,000 foot level and kind of go down to sea level. Based on what Prith shared, it's probably more the 20,000 foot level where I'll start and go down a little bit. But I do still want to kind of give a little bit of context for why we're interested in the Julia languages. And as you'll see, it's kind of similar to the what may be considered smaller building blocks that you wouldn't think maybe matter at the high level, the digital engineering landscape level. But they do, and that's kind of the point I'll try and make today, is that those building block pieces really do matter and they can help. So I'll talk about that landscape, a little bit of the ANSYS view on it, and digital twins in particular, and what it takes to bring digital twin solutions to market, the issues that arise in that, and where Julia can help smooth some of that out. When I kind of at first thought about this and was putting it together, I was thinking of it from a software development or a product development perspective. It turned out to be probably more of a model-based engineering perspective. And I'll blend those two viewpoints a little bit together throughout, and I'll apologize, I won't really differentiate as I'm blending. But there's a lot of parallels back and forth between them that I think are relevant and that I show here. So, you know, in software development, different developers are going to have different favorite languages or tools that they use for prototyping. Same thing in model-based engineers with different tools or products that they may prototype with. But that leads to those languages likely being different than the production language that you need eventually to code in. Or if you're doing diagramming-based languages and model-based engineering, that may be different from an analysis language that you use. And then, because those are different, you're going to maybe have to do translation at some point, the two-language problem, or you're going to have to be co-simulating between different models and environments in a model-based engineering environment. And then when you want to loop that back, you have to go through all of it again. So if you want to enhance your existing code base or add new features, you may go through all this exercise again. And what we'll talk about here with the digital twins and model-based engineering, you want that digital twin to feed back information to the beginning of your process. So seemingly small issues that may arise at each of these steps can easily derail the whole pipeline or the whole workflow. And so the question I kind of set out to answer myself, and I'm working on with some colleagues at ANSYS, is to see where Julia could help smooth out some of those wrinkles. Okay. The point of the digital engineering landscape is to bring in digital tools to improve ROI across the product lifecycle. So R&D phase, deployment, operations, disposal, all of these type of things. And there's a couple of different strategies you can take. You can do the shift left strategy, where you bring the digital tooling earlier in the process into the design phase, or you can do the shift right, where you're emphasizing it more in the verification validation stage, doing things like uncertainty quantification and those type of things. Both are valuable, both together are more valuable, and so we definitely want to do both of those. So like I said, twin AI is for building digital twins, just to kind of set the context as that term can be used and thrown about differently. This digital twin consortium definition here, a virtual representation of a real-world entity or process synchronized at a specific frequency. So it's a digital representation, and it's somehow synchronized with the physical asset. That's the definition we kind of use and base off of. You can see the different values that different people will gain from that, but it can be anything from the design all the way through to informing your next design. So through the design, validation phase, operations phase, and then into the next design. And so because of that idea and this kind of shift left, shift right in the digital engineering landscape, the idea of what's a digital twin has also kind of expanded. And you'll hear talked about in industry these different types of digital twins, or a digital prototype, a digital shadow, a digital twin. The idea being the original value seen in digital twins can be expanded earlier, and you can start recognizing that value with the digital prototype, which would be in the design phase, where maybe before that was just thought of as a system level simulation, and maybe it still is, but if it's connected through that whole life cycle to a digital twin at the end, and it's started with planning in mind of it becomes a digital twin, you're basically building your digital twin at the same time that you're building your product, and they're evolving and growing together, to the digital shadow stage, where you're have a one-way connection, where you're bringing in data from testing and evaluation maybe to improve and inform your digital shadow, to the digital twin, where you have the two-way connectivity with the asset, where they're both communicating back and forth. Okay? If you look at what this how this plays out on the traditional engineering V cycle, in the gray you have the traditional activities, concept definition, system requirements, down to system modeling, more detailed modeling, up through verification and validation to operations. The life of the digital prototype shadow twin follows that same process. So you have the digital prototype over here on the left, the digital shadow with the one-way connection when you're doing your verification validation, up to the operations where you have the digital twin. Here, basically the same view, just mentioning it, you'll hear it talked about a little bit differently maybe in the aerospace and defense sector. The DoD instruction here, 5000.61, which was laid out verification, validation, and accreditation for simulation models, speaks to a lot of these ideas, but also makes them essentially requirements when you're in the FA&D space, that if you want to be a simulation tool in that space, you have to meet these accreditation levels, and that goes, again, all the way kind of across that whole spectrum, where it may just start at the system level modeling through to the more detailed component level modeling and up into manufacturing, operations, and sustainment, and then loop all that information back down for the next cycle. Prith also mentioned this morning, so I'll just touch on it briefly, but the idea of a hybrid digital twin. I guess to give a little bit of context to that, you could have, like Prith talked about this morning, you could have just a purely analytics digital twin that's based on data. You collect data, you build a data model out of it, that's your twin. You could have a purely simulation physics-based twin, where you take your first principle of physics and you say, I know this is how it's supposed to behave, I'll write down my equations, I'll simulate it, that's my twin. A hybrid twin is a combination of both of those approaches, where they both have their benefits and drawbacks, but the best approach is to leverage all of the information you have available. If you only are looking at data, there's probably something you know from first principles that you could be leveraging. But if you're only looking at the physics, then you're throwing away your data. And the best approach is to take all of that together. And the engineering knowledge I'm talking about here is whatever you learn in your engineering process, from specifications, tolerances, those type of things. So you take all those together, throw them together, and you get a hybrid digital twin that leverages everything you know about your system or asset. And the benefits you gain there are a lot, but these are probably the four main ones. Virtual sensors, so your twin learning from whatever sensor information you do have, being able to predict other information that you don't have from physical sensors, essentially, so extending out what you can censor in your system. the predictions that you have grounded on your first principle physics. You have some base level of grounding that's modified by the data you learned from, being able to apply what-if scenarios so you can treat your digital twin as a sandbox environment you may, and kind of connected with this causality and failure as well. You don't want to do everything in testing because you may break your system. You can push your digital twin into those failure regions that you don't want to actually do on a physical asset. Okay, and so what that means is you have to do basically what we've heard in other talks, what SciML does, and the idea of this hybrid digital twin. You have to combine those two approaches numerically as well. So you have the solvers that are encapsulating or simulating the physics knowledge. You have all of the machine learning methods that come in from the data side, and you want to combine those in some way so that you have a single twin, and then you have to deploy and scale it from there. Okay. Now, to try and start drilling down to a little bit of a lower level here, and what does that actually entail? So that's the big idea. How do we actually go about doing that? Showing here two paths, and these are the two paths that we commonly see users going on. You can think about it often is a green field or brown field scenario, and I'll explain what that means. So on the top path going down into the middle, the 0D or 1D system simulation path, that will be often followed by people that don't have CAD geometry or don't have the ability to simulate at high fidelity their asset, but they can throw together a system model. So that could be a brownfield scenario where you may have an asset from 1970, you have no idea what the geometry was when it was originally built, and even if you did, it's changed a lot since then. So you don't have any of that original engineering information. You just know the kind of the current layout. So you build a system level model of it. It's old, so you have a lot of data from it. You take that data, you use it to calibrate your system model and build it into a hybrid digital twin with the combination of what you know from simulation and the data. On the flip side, and more maybe like a greenfield situation where you're starting from scratch, you do have modern tooling, CAD drawings, CAE engineers that can simulate all of these things. You build that up from the 3D level up, create reduced order models so that you can actually simulate it in something like real time, and build your twin that way. Better yet, and probably more common, is there's some combination of those two approaches where you're using both to create a twin. The challenges you're trying to meet in that process, or at least these four things here. In simulation, you're always going to have an accuracy versus speed trade-off, but you're trying to maximize those both as much as possible. Different scenarios, maybe we'll emphasize one more than the other, but you're always going to have to worry about that. In a digital twin environment, you want to often simulate it in real time or order real time, but get as much physics and accuracy in as possible. Adaptability, so I talked about these brownfield scenarios. If you deploy your twin, it may work perfectly on day one, but as things age and degrade and such over time, the twin may deviate hugely from that original behavior. So you need to be able to adapt it on the fly so that you don't have to go back and rebuild it every time. And the flexibility to be able to apply different drive scenarios if you're talking about a vehicle, different operating scenarios, and scalability. Think about if you have a fleet, and this kind of speaks to the adaptability as well. You have a fleet of vehicles, you would deploy a digital twin with each of them. They're all going to evolve differently. You have to scale across that, but you also have to have each one adapting to each, uniquely to each member of the fleet. So as you're traversing this digital prototype shadow twin V here, or cycle, where do difficulties often arise? One is up in the kind of the early MBSE stages that I won't talk too much about today. I haven't investigated that in the context of Julia, so I won't talk too much about it, but connection to requirements. Another big one now then is stitching all of these different solutions together. So if you have a perfect solution at each stage along the cycle, that's nice, but it doesn't necessarily give you much if you don't have a way to connect those through. the two-language problem with code translation or the code simulation again, the speed fidelity solver, speed and fidelity trade-offs that I just talked about, the hybrid modeling, how are you going to bring the data in, what are you going to do with it, how are you going to connect it to the simulation. And I also won't talk too much about the bottom, again, because I haven't explored it in the context of Julia, but then you've got the connection to all the IoT pipelines and infrastructure if you want to deploy your digital twin. So then with all of that, where does the motivation come to try Julia? Speed, of course, is a big one. Prototyping, so using Julia as a prototyping environment is very attractive to us, so that you have a ready-made prototyping environment that you can take to production, but also hopefully that developers can kind of coalesce around and use together, as opposed to having disparate tools. As a system modeling environment, so the modeling toolkit, and again here you can see I'm kind of blending between the developer and model-based engineering perspective, but lots of attractive things in both of those. In the system modeling, model-based engineering, being able to do things like modeling toolkit to have those models that execute with speed but also have some fidelity to them, give you faster digital twins. And then the SciML ecosystem, like I mentioned a little bit ago, basically identical value proposition to what I was talking about with hybrid digital twins, being able to combine the numerics with solvers and machine learning. And again, with just this last point here, which I'll probably mention a couple more times, if you have a common language or set of tools that you can use across this, that really helps smooth out the whole process. So I'll just touch briefly on a couple of things I've looked at here. The first one was speed. So FMUs are a big part of being able to simulate different components in a digital twin at a system level. You're often bringing in models from different users, maybe even different companies. If you're talking about an OEM and supplier, those will often come in as an FMU. You need to be able to solve those. If we can solve them faster and better, that's certainly to our benefit. So just showing here across a different range of physics and applications, using using FMI.jl, but essentially built on differential equations.jl, the improvement that we got on these FMUs. So you can see there for the most part, Julia did better. There's a couple where it struggled, but I'll point out these were all very difficult FMUs to simulate. That's why they were chosen. So none of these were easy to simulate. They were all difficult problems. And this is even a little bit of an older benchmarking I did. There may have been improvements where it would do better now. But very happy with the results here, where you can see that for the most part, the improvement was a lot. The simulation speed improvement was a huge gain over what we had. Also point out, this is not comparing to any single solver. This is comparing to what was the best solver known for that particular model in the past. So in a way, it's not apples to apples, but the point is what's the best we can do for this type of physics and this model. In most cases, Julia did better. The computational power behind Julia as well, so just showing here a kind of full vehicle model where a lot of different components again interacting. We had trouble compiling essentially a raw model for the motor component, where it's a very good model, but it ends up being a large matrix, large pieces underneath that we were having trouble compiling. And the Modelica compilers we tried, it would take over 2 hours. Julia did it in about 2 minutes with packagecompiler.jl. So again, huge benefit there. In the digital twin space, and if you're thinking of building a pipeline to automate or build digital twins automatically, I mean, two plus hours is intractable. You really can't work with that, but 2 minutes is fine. The 1D modeling here with the modeling toolkit, I mentioned this. This is an exercise I started, was happy with, and never really finished. I moved on to other things, so I don't have any specific benchmarks here to show, but I recreated some battery ECM components, equivalent circuit models in Julia compared to Modelica and other languages we had. The performance, or the results were just as accurate, the performance much faster. This is probably something I'll return to scale it out to large numbers of cells and large battery packs. But from what I had seen already, I was very happy with the performance gain here. And then the last example here, talking about the SciML ecosystem. So again, this picture of hybrid combining data, machine learning, and physics simulation. We took a, so kind of tell the story behind this, we had an engineer that came with a method and said, hey, this method I've created is better for this specific application than the other methods that we have in-house. What can we do to get it in product? We had that come up several times, and it goes through the development process, we get it into the product. Did this with Julia, and it went through a order of 2 times faster because we didn't have to take it from the language that was prototyped in and translated it. We were able to take it directly from Julia, compile it, and get it ready for the product. Just a couple of areas for improvement that we've seen, and these are all known and being worked on, I know, by different members of the community. Compilation size and time, system image, and system libraries, and the second one, FMU. So those are both big things for us. If the performance is really good in the end, that's great. But if the compilation size is too big, it's hard to put it in a product, and if it takes too long, it's hard to put it into a development process. If the time to constantly be recompiling as you're developing takes too long. And then the FMU generation, again, has to be as small as possible to fit into a digital twin. And then library content, I won't talk too much about that, but the more you have available at your hands in the prototyping phase, the better. So just kind of close out here on this slide and the next, showing what's needed in software development and model-based engineering, or at least a few things that are needed across the prototyping to production workflow and where Julia can help. Certainly not claiming that this is the only way Julia can help, just kind of the things that we've found. I emphasize with that last point over here on the left side, this prototyping. Just my kind of personal opinion, I guess that's huge if you have an environment where you can easily sandbox things, try out new solutions. You have different algorithms available at your fingertips. If you're doing model-based engineering, you have different libraries and blocks and things you can play with. At that stage, that's big if you can carry it throughout the rest of the workflow. And that's where the single language, if you can do that in Julia, have consistent APIs across their consistent environment, that's huge and can really help speed things up. So I posed the question, can Julia iron out some of these wrinkles? From what I found it can. There's a few things that still need to be ironed out with the compilation size, time, those type of things. But largely, I'm very happy with how Julia's been able to help in our development workflows. Thanks for listening. That's all I have.
Thank you so much. So we have time for questions.
I think early on in one of your slides you mentioned as a sort of, I don't know if it was a requirement per se, but it was something that was important was requirements. But I don't think, maybe I missed it, and I don't think you talked about how requirements would feed into this. Or did I miss it?
Yeah, so we're looking at that now, haven't got into it, but the idea of going from a system architecture level down into the system modeling level. So I basically talked about connecting from the system modeling level through to a digital twin. That's great. It's missing that piece of the system architecture before that. If you can go from a system architecture model directly to a system model, either somehow having a connection there, being able to kind of automatically propagate those requirements down and simulate them, get the results back and propagate them back up. System level engineers would be ecstatic if that solution existed.
Okay.
Do we have more questions?
So you had a slide showing sort of speed up with differential equations or JL. against sort of best-in-class other products. Do you have a sense of, the variance in the numbers there, right? Some you said were 300x, some were 19x, some was...
The benchmarks, is that what you're talking about?
Yes.
Yeah.
So do you have a sense of, what's the variance from? Is it sort of domain knowledge? Is it methods? Is it, engineering stuff? A sense of, what causes the differences in sort of the speed ups that you see, just from having, run all of this, really?
Yeah, a large part of it is probably what I talked about where, so it's not necessarily the same solver within differential equations, .jl from line to line, and it's not the same solver that's being compared to. In some cases, these were very domain-specific solvers, like I think the rectifier, for example, where it did a little bit better than Julia. That was a very domain-specific solver that would not have performed as well probably anywhere else, but was written specifically for that. So in a way, it's not fair apples-to-apples comparisons, like I was saying. But that's probably a big reason for the variance, and just these were not randomly selected, but just the hardest FMUs we could find. There was no systematic way we chose them. We just, the hardest ones that kind of had failed to simulate in the past, we pulled those out.
Thank you.
Yeah.
More questions? Okay.
Hi, this is a great talk. I had another question related to this slide in particular. I noticed that there was a hydraulic model that's failed. Could you speak to the nature of that failure? What was basically required?
The solver crashed. It couldn't execute the next time step essentially. I had looked into it a little bit at the time. I've forgotten exactly what it was. That's one where maybe if we could work on it a little bit, we could get it to finish to completion. But just straight out of the box, the solver got to a point where it couldn't step into do the next time step.
Are these models shareable? Or
Ron John has
or
been
rather,
helping with some
at
of
least
them.
with Chris's team or even open source public, either ways.
Yep, happy to share.
Okay, so with that, let's thank Matt. And that's a wrap on this session. And I'll see you all tomorrow in this room. Enjoy Pittsburgh and the social activities now.